In 1942, a U.S. Navy sonar operator watched what appeared to be the ocean floor rising toward his ship from hundreds of meters below the Pacific. It moved slowly, consistently, every night. The Navy thought they had discovered a hidden layer of seafloor. They hadn't. What they were actually seeing was alive, and it is still rising toward the surface every night as you listen to this. The Twilight Zone, stretching from roughly 200 to 1,000 meters below the ocean surface, contains more living creatures by weight than every human being on Earth combined. It is one of the largest living spaces on the planet, and we have explored almost none of it. By 200 meters, nearly all sunlight is gone. Cameras stop working naturally. Pressure climbs toward 100 atmospheres. Animals made almost entirely of water collapse or dissolve before reaching the surface. The deeper scientists study this zone, the less the data agrees. Sonar detects vast moving layers that nets barely capture. Nets retrieve animals cameras never see. Entire populations appear and disappear depending on the tool being used to observe them. Some species sense approaching equipment before it arrives. Others trigger waves of bioluminescent alarm signals the moment artificial light enters the water. And every night, billions of creatures rise through the darkness together in the largest migration on Earth, helping regulate the climate of the planet in ways science only recently began to understand. Today, we descend into the ocean's twilight zone to understand why one of the largest ecosystems on Earth still defeats almost every instrument we send into it. But before we begin, I'm curious, is this your first time here, or have you been down this rabbit hole with us before? Let me know in the comments. Now, let's descend into the ocean's twilight zone and the living wall rising through it every night. Far above the seafloor, long before the trenches and volcanic plains begin, the ocean changes in silence. A descent through open water is not a passage through emptiness, but through layers, each one holding its own climate, chemistry, and forms of life. The sea appears continuous from the surface, smooth beneath the wind and moonlight, yet beneath that moving skin, it separates itself into stacked worlds, arranged vertically through darkness and pressure. Closest to the air is the sunlight zone, extending from the surface down to roughly 200 meters. This is the bright ocean of coastlines, storms, reefs, and drifting plankton. Nearly every form of marine life depends on it in some way, because this is where sunlight still carries enough energy for photosynthesis. Every floating phytoplankton cell, every ribbon of algae, every vast bloom spreading green across satellite imagery survives within this narrow upper band. The entire biological engine of the ocean begins here, suspended inside the reach of light. But light does not travel far in seawater. Red vanishes first, disappearing within the upper few meters until blood becomes black underwater. Orange and yellow fade soon after. By 50 meters, much of the warm spectrum is already gone, stripped away molecule by molecule as the ocean absorbs it. What remains sinks downward as a dim blue residue, colder in tone with every meter descended. At 200 meters, less than 1% of surface sunlight survives. Even that faint illumination feels exhausted, thin and diffuse, unable to sustain plant life any longer. The ocean does not announce the boundary with a visible line. There is no sudden wall between one world and the next. Instead, the character of the water slowly alters until the transition becomes undeniable. This is where the twilight zone begins, suspended between brightness above and total darkness below. The temperature changes with it. Descending through the thermocline feels less like moving deeper into water and more like entering another season entirely. Near the surface in tropical regions, Temperatures may rest near 20 degrees Celsius. Farther down, toward 1,000 meters, the water cools to 4 degrees. The shift does not happen evenly. It arrives in steep pockets and invisible gradients, layers of cold folded beneath warmer water, like submerged weather systems drifting in darkness. Pressure rises with relentless precision. At 200 meters, 20 atmospheres press inward from every direction, nearly 300 pounds against every square inch. By 1,000 meters, the pressure reaches 100 atmospheres, more than 1,400 pounds per square inch. Human bodies were never shaped for conditions like these. Every instrument lowered into the mesopelagic enters an environment actively attempting to crush it closed. Below the twilight zone lie deeper provinces still. The midnight zone stretches downward for several thousand meters beneath perpetual darkness. Farther still rests the abyssal zone, immense plains of near-freezing water spread across the ocean floor. Deeper than all of them are the Hadal trenches, narrow fractures descending into the crust itself. Yet despite the enormity of these deeper regions, the twilight zone occupies the greatest living volume of the ocean. Measured three-dimensionally, it contains roughly 95% of the planet's habitable marine space. For most of scientific history, almost nobody paid attention to it. There were no reefs to map, no sunlight to photograph, no profitable fisheries close enough to exploit easily. Nets returned damaged fragments from depths that seemed impossibly distant, and early instruments could barely survive long enough to transmit useful information. The twilight zone remains suspended outside ordinary observation, too deep for surface biology and too shallow for deep ocean mythology, existing quietly beneath the shipping lanes of the world while almost everything about it remained unknown. Long before anyone understood what moved beneath their ships at night, naval sonar operators began noticing a strange behavior in the Pacific. The echo beneath them behaved like the seafloor, broad and continuous, stretching across enormous distances with the solidity of submerged terrain. Yet after sunset, the boundary drifted upward through the water column. Before dawn, it sank again into deeper darkness, repeating the motion with such consistency that crews first suspected machinery, then enemy submarines, then instrument failure. The phenomenon received a technical name before it received an explanation. The Navy called it the deep scattering layer because sonar pulses striking it scattered back toward the surface as though they had collided with stone. During daylight hours, the layer usually rested several hundred meters down, often between 300 and 500 meters beneath the waves. At night, it climbed upward until it hovered astonishingly close to the surface, sometimes within 50 meters of open air, before retreating again with the arrival of morning light. What unsettled researchers most was not simply the motion, but the scale. The same behavior appeared in every ocean where measurements were taken. Atlantic vessels recorded it. Pacific fleets recorded it. Instruments lowered into the Indian Ocean encountered it as well. Entire expanses of the planet seemed to breathe in synchrony beneath the sea surface, rising and sinking according to a timetable older than ships themselves. After the war, improved sampling and acoustic studies finally revealed the source. The false bottom was alive. It was composed of immense concentrations of fish, squid, shrimp, and drifting crustaceans packed densely enough to imitate geology on sonar screens. Many carried gas-filled swim bladders inside their bodies, tiny reflective chambers that returned acoustic signals with remarkable strength. A sonar pulse striking billions of these organisms at once produced an echo almost indistinguishable from solid ground. Yet the deep scattering layer was never a single wall of animals. It behaved more like weather, a shifting vertical continent assembled from hundreds of species moving together, while still remaining separate. Different organisms occupied different depths within it, forming stacked bands that changed subtly with latitude, season, cloud cover, and lunar phase. In some regions, the layer thickened until it became acoustically impenetrable. Research crews occasionally lowered anchors toward what sonar interpreted as shallow bottom, only to discover hundreds of meters of open water still waiting beneath. Among the most important inhabitants were the lanternfish, delicate mesopelagic fish belonging to the family Myctophidae. Most measured only a few centimeters long, slender enough to disappear into darkness almost immediately after capture. Along their bodies ran organized rows of blue-green photophores, small organs capable of producing cold bioluminescent light. Seen in darkness, they resembled fragments of drifting constellations suspended in seawater. Their abundance is difficult to picture clearly because it exceeds almost every familiar comparison. Lanternfish may account for roughly 65% of all deep-sea fish biomass on Earth. Their total population likely reaches into the hundreds of trillions. Only the bristlemouth fish may outnumber them among vertebrates. Yet despite this staggering dominance, they remained almost entirely absent from public awareness, hidden within a zone few humans ever considered. Even now, the deep scattering layer resists prediction. Modern sonar systems still struggle to model its movements accurately because the layer responds to so many interacting conditions at once. Moonlight alters its depth. Seasonal productivity alters its density. Regional temperature gradients shift its structure. In one stretch of ocean, it may rise rapidly after dusk, while elsewhere it remains deeper through the night, for reasons still poorly understood. What the Navy discovered in 1942 was not merely an acoustic illusion beneath the Pacific. It was the first indication that the Twilight Zone was densely inhabited on a planetary scale, not an empty corridor between surface waters and the abyss below. Beneath the shipping routes and weather systems of the world existed an immense living structure, moving together through darkness with enough collective mass to impersonate the seafloor itself. For a brief period each evening, the open ocean hesitates between day and night. The surface loses its sharpness, colors flatten into silver and blue, and sunlight weakens just enough for something ancient to begin moving upward from below. Across the Pacific, the Atlantic, the Indian Ocean, the Southern Ocean, beneath calm seas and storm systems alike, an immense ascent begins almost simultaneously through the water column. The trigger is light alone, not temperature, not tides, not chemical trails drifting through the currents. The movement begins when the final traces of daylight sink beneath a threshold invisible to human perception, but unmistakable to the organisms suspended in the twilight zone. As the last photons fade overhead, billions of animals detach from the darkness beneath them and begin to rise. The distances involved are enormous for bodies so small. Lanternfish, bristlemouth fish, copepods, amphipods, krill, surgested shrimp, and drifting squid climb upward hundreds of meters through cold water in only a few hours. Some species travel from depths approaching 800 meters to waters just beneath the surface before descending again before dawn. Relative to body size, the journey rivals a human running a marathon every day without pause, sustained over an entire lifetime measured in darkness and pressure. The reason is simple and unforgiving. In open water, there are few places to hide. During daylight hours, visibility belongs to predators. Tuna, dolphins, seabirds, larger fish, and squid hunt most efficiently when sunlight outlines movement against the blue above. For small mesopelagic animals, survival depends on remaining deep enough to disappear from sight. Night changes the balance. Darkness softens the reach of vision, allowing creatures from the Twilight Zone to approach the nutrient-rich surface waters safely enough to feed. Yet the migration is not a chaotic swarm rushing blindly upward. It unfolds with extraordinary structure. Different species occupy distinct vertical bands, ascending to precise depth windows that remain remarkably consistent within each region of ocean. One layer of krill may stop beneath another layer dominated by lanternfish. Certain squid remain deeper, while copepods drift higher toward the surface film. The entire migration resembles a living atmospheric system stacked in moving strata, shifting subtly with latitude, season, and lunar brightness. Moonlight itself alters the pattern. On brighter nights, many species remain slightly deeper, holding beneath the reach of increased visibility. During new moons, they ascend farther upward. Even cloud cover can influence the upper limit of the migration. The ocean responds to faint changes in illumination with astonishing precision, as though the entire water column were calibrated to the movement of distant celestial light. The migration also transports something less visible than flesh. Near the surface, these animals consume phytoplankton, drifting organic debris, and the countless microscopic organisms supported by sunlight above. The carbon absorbed by surface life enters their bodies during feeding. When the animals descend again into deeper water, they carry that carbon with them into the Twilight Zone. There, through respiration, waste, and death, the carbon is released far below the upper ocean layer that exchanges gases directly with the atmosphere. Oceanographers call this process the biological carbon pump. It functions continuously beneath the sea surface, lowering carbon into deeper water where it may remain isolated from the atmosphere for decades or longer. The scale of the transport is immense. Current estimates suggest this nightly migration moves between 1 and 5 billion tons of carbon downward every year. Much of it passes silently through animals no larger than a finger, drifting through darkness beyond ordinary human sight. Entire climate systems are influenced by movements that remained largely unknown until surprisingly recently. Although fragments of the migration had been observed for decades through sonar and scattered net samples, its full planetary scale was only confirmed during the 20th century as oceanographic instruments improved across multiple basins. Its role in regulating carbon emerged even later, becoming clear only in the 21st century, as researchers began tracing the hidden pathways connecting twilight life to the chemistry of the atmosphere itself. For most of oceanographic history, knowledge of the Twilight Zone arrived tangled in wet mesh beneath research vessels. Nets were lowered into darkness on cables thousands of meters long, drifting silently behind ships through water too deep for direct observation. When they returned to the surface hours later, scientists sorted through whatever remained inside and assembled an understanding of the hidden ocean from damaged fragments lifted briefly into daylight. The method appeared straightforward. Drag a net through the water column, collect what lives there, measure the catch, and estimate abundance from the volume sampled. Entire catalogs of mesopelagic species were built this way. Biomass calculations, migration estimates, and early climate assumptions all emerged from these collections. Yet the deeper researchers looked into the Twilight Zone, the more apparent it became that the nets were not revealing the ecosystem accurately. They were filtering it through layers of distortion before it ever reached the deck. The first distortion begins before contact occurs. Mesopelagic animals have evolved within a world where survival depends on detecting movement in darkness long before danger arrives. Many species sense subtle pressure changes propagating through the water ahead of an approaching object. A trawling net may seem passive from the surface, but underwater it pushes a bow wave through the ocean like a slow underwater storm front. Small fish and crustaceans often detect this disturbance several meters away and veer aside almost instantly, slipping around the mesh before capture becomes possible. The animals least capable of escape are therefore not necessarily the most abundant. They are simply the slowest to react. The mesh itself creates another absence. Nets must allow water to pass through them, or the drag becomes impossible to manage at depth. This means openings remain between the woven fibers, large enough for countless organisms to slip through unnoticed. In a region dominated by life measured in millimeters and centimeters, entire biological communities disappear through these gaps uncounted. Larval animals, delicate planktonic forms, and transparent drifting species pass back into darkness without ever entering the scientific record. Then comes the ascent. A net pulled upward from several hundred meters carries its catch through rapidly changing conditions. Pressure decreases continuously, temperatures rise, water chemistry alters minute by minute as the net climbs toward the surface. Organisms adapted to stable deep water pressure begin failing almost immediately. Gas bladders expand violently, soft tissues rupture, some bodies bloat grotesquely, while others collapse inward. Transparent animals lose structural integrity altogether, dissolving into gelatinous residue before the net breaches the waves. This problem reshaped the history of deep-sea biology more than most people realize, because many Twilight Zone animals are composed almost entirely of seawater. Salps, siphonophores, ctenophores, and numerous jellyfish species possess bodies so delicate that traditional nets reduce them to nearly nothing. A creature several meters long may leave behind little more than mucus threads and cellular debris, impossible to identify afterward. For centuries, these organisms remained effectively invisible to science, not because they were rare, but because the primary tools used to study the ocean destroyed them during collection. Even today, many species known from the mesopelagic exist only as partial remains preserved in laboratory archives. A jaw detached from its body, a scale reflecting dim blue light beneath a microscope, a single photophore separated from the animal that once carried it through darkness. The full scale of the discrepancy became impossible to ignore in 2014 when researchers compared net trawl biomass estimates directly against acoustic measurements gathered simultaneously from the same regions of ocean. Sonar consistently indicated vastly more life than the nets recovered. In some cases, the acoustic estimates were 10 times higher than the biological samples suggested. That difference altered the meaning of the Twilight Zone entirely. The gap between 1 billion tons of fish and 10 billion tons is not a minor statistical correction drifting quietly through scientific literature. It changes carbon transport calculations, food web structures, and the estimated influence of mesopelagic life on the climate itself. Every major estimate of Twilight Zone biodiversity and biomass had been built upon net data, and almost all of those estimates now appear to lean in the same direction, toward absence, toward undercounting, toward a hidden world far larger than the tools designed to measure it. At first, cameras seemed like the answer to everything the nets could not solve. If fragile animals dissolved during retrieval, then perhaps they could simply be observed where they lived, drifting intact through the cold interior of the ocean. Engineers built remotely operated vehicles wrapped in steel housings and lowered them slowly into the mesopelagic with floodlights, thrusters, manipulator arms, and high-resolution lenses pointed outward into darkness. But the Twilight Zone is not a passive landscape waiting to be photographed. It is an ecosystem shaped by sensitivity to light itself. Long before the vehicle enters visual range, its presence spreads through the water as vibration, electrical activity, and hydraulic noise. Then the lights arrive. In the upper ocean, artificial illumination may disturb marine life briefly before behavior normalizes again. In the twilight zone, where most organisms communicate, hunt, hide, and survive through bioluminescent signaling, a sudden burst of bright white light functions less like observation and more like an explosion. One animal detects the intrusion first. A shrimp flashes. Nearby fish respond with pulses of blue-green light. Another organism reacts to those signals and emits its own burst farther into the water column. Within seconds, a chain reaction propagates outward in every direction around the vehicle. Researchers call this the alarm cascade, a spreading sphere of artificial behavior triggered entirely by the observer. The camera records all of it in extraordinary detail. Yet what appears on the monitor is no longer ordinary Twilight Zone behavior. The animals are reacting to disturbance, not continuing the routines they would have followed in darkness. Predators scatter or freeze motionless. Prey species alter their swimming patterns. Organisms that normally remain invisible illuminate themselves in warning flashes never intended for human eyes. The deeper researchers looked into the footage, the more difficult interpretation became. Every image carried uncertainty embedded inside it. Was an observed movement natural behavior, or a response to hydraulic noise from the thrusters several meters away? Was a bioluminescent pulse communication between animals, or a stress reaction triggered by the vehicle itself? The act of observation reshaped the environment before the first frame was even captured. Transparency created another problem entirely. Many Twilight Zone animals evolved bodies with almost no pigment or opaque structure. In dim blue water, their tissues scatter so little light that they effectively vanish against the surrounding ocean. Standard cameras, even sophisticated modern systems, struggle to distinguish these organisms from the darkness around them. Entire communities drift through the field of view unnoticed because the lens cannot separate transparent tissue from open water. For decades, researchers reviewed footage believing certain regions of the mesopelagic were sparsely inhabited. Then, polarized light imaging systems developed during the early years of the 21st century revealed something startling. Waters that appeared empty through conventional cameras contained dense populations of transparent animals previously invisible to observation. Delicate ctenophores, drifting larval forms, gelatinous predators, and nearly transparent crustaceans emerged suddenly from what had once looked like vacant ocean. The discovery suggested that years of recorded footage had overlooked living organisms not because they were rare, but because the cameras themselves were blind to the optical strategies evolution had produced in darkness. Time imposes limits as well. Most remotely operated vehicles operate through long tethers connected to surface ships, drawing power through cables while fighting pressure, currents, and battery constraints. At mesopelagic depths, many missions last only several hours before recovery becomes necessary. Yet the vertical migration unfolding through the Twilight Zone spans an entire cycle of dusk, night, and dawn, stretching across much longer periods. A vehicle observing one moment often misses the rest of the movement entirely, and the scale remains overwhelming. The Twilight Zone extends across hundreds of millions of square kilometers of ocean and nearly a kilometer of vertical depth. A single vehicle surveying one location for one day samples a volume so tiny that researchers sometimes compare it to examining a single bacterium on a field of grass and attempting to describe the entire ecosystem surrounding it. Despite decades of expeditions and thousands of hours of footage, fewer than 1/5 of known mesopelagic species have ever been observed alive in their undisturbed environment. Most remain known only through fragments, brief encounters, or passing flashes inside water still resisting direct observation. The descent into the twilight zone begins gently from the surface. Cables unwind smoothly from research vessels, instruments slip beneath the waves without resistance, and the ocean appears almost calm in its acceptance of what is entering it. Yet with every meter downward, the water grows heavier, not metaphorically, but physically, steadily, with absolute consistency. The sea presses inward from all directions at once, increasing force upon every exposed surface without pause or relief. At 200 meters, near the upper boundary of the mesopelagic, the pressure has already reached 20 atmospheres. Nearly 300 pounds press against every square inch of metal, glass, wiring, and seal. By 1,000 meters, the force reaches 100 atmospheres. More than 1,400 pounds, pressing continuously inward. Every research instrument lowered into this environment must preserve a tiny pocket of ordinary surface conditions inside itself while enduring pressures 100 times greater outside. Nothing about this balance is natural for engineered systems. Titanium pressure housings contract slightly under load. Syntactic foam compresses almost imperceptibly. Optical viewports flex inward by microscopic amounts, difficult to predict completely in laboratory conditions. Every connector linking one component to another becomes a potential weakness because different materials respond differently under compression. A seal that appears flawless at the surface may distort enough at depth to admit a slow intrusion of seawater molecule by molecule. The thermocline complicates the problem further. During descent, instruments often pass rapidly through layers where temperature drops from warm surface conditions toward near-freezing water. Metals, polymers, ceramics, and glass all contract at different rates as they cool. A junction stable during testing in controlled laboratories may begin separating subtly under the combined effects of pressure and temperature change. Engineers describe deep-sea systems as pressure tolerant, but tolerance is rarely absolute. It is negotiated continuously against forces capable of exploiting microscopic imperfections. Even the sensors designed to study the ocean become unreliable under these conditions. Transducers measuring sound behave differently when compressed. Optical instruments shift calibration slightly under pressure. Chemical detectors alter sensitivity depending on temperature and depth. Every reading collected from the mesopelagic passes through correction algorithms intended to compensate for these distortions, yet each correction introduces additional uncertainty. The deeper the observation, the more interpretation becomes inseparable from measurement itself. The organisms living there experience these conditions not as extremes but as normality. Their tissues evolved within pressure fields, stable across evolutionary time. Bringing them upward toward the surface reverses the balance catastrophically. As retrieval containers rise, dissolved gases trapped within animal tissues begin expanding. Gas bladders swell violently. Pressure-adapted cell membranes rupture under changing chemical gradients. Some fish emerge, bloated and damaged beyond recognition. Gelatinous animals collapse into shapeless masses within minutes. Others appear physically intact, but die almost immediately after surfacing because the molecular systems governing respiration and buoyancy no longer function outside their native pressure environment. Researchers have attempted to solve this problem using pressurized collection chambers capable of maintaining deep water conditions during ascent. These devices function like miniature submersibles attached to sampling systems, preserving internal pressure while returning specimens to the surface intact. The engineering challenge is immense. Every seal, valve, and pressure boundary must remain stable throughout ascent, while containing organisms evolved for conditions difficult to reproduce even briefly. Successes remain rare and technically fragile. The violence of pressure failure became newly visible to the public during the Titan submersible implosion in 2023. Under extreme compression at depth, structural collapse occurred almost instantaneously. The surrounding ocean moved inward faster than human reaction time itself. Deep pressure does not break systems gradually. Once failure thresholds are crossed, it erases them. Because of this, oceanographic instruments designed for long-term mesopelagic deployment are extraordinarily expensive. A single sensor package rated for sustained operation at depth may cost hundreds of thousands of dollars before deployment even begins. Meaningful sampling across the global Twilight Zone would require thousands of such systems distributed through an ecosystem spanning most of the planet. The difficulty is not simply reaching the Twilight Zone. It is surviving contact with an environment that applies relentless force to everything sent into it, living or mechanical alike, until even the smallest weakness eventually gives way. In the Twilight Zone, survival rarely belongs to the strongest animal in the water. It belongs to the least visible. Across millions of years, evolution transformed the mesopelagic into a place where concealment became more valuable than armor, speed, or size. Bodies thinned, pigments vanished, eyes enlarged, and light itself was reshaped into camouflage. Nearly every creature drifting through the zone exists within a continuous negotiation between detection and disappearance. The darkness there is incomplete. A faint residue of blue light still filters downward from the distant surface, weak enough to conceal, but strong enough to betray a silhouette. Any animal viewed from below risks becoming visible against that dim glow overhead. To survive, many mesopelagic species evolved one of the most precise forms of camouflage known in nature: counterillumination. Lanternfish and hatchetfish carry rows of bioluminescent organs along the undersides of their bodies. These photophores emit carefully regulated blue-green light downward into the water beneath them. The brightness is calibrated so precisely that the animal's outline dissolves against the faint illumination filtering from above. Seen from below, predator and prey alike disappear into the background glow as though their bodies have been erased from the ocean entirely. The hatchetfish refines this strategy even further through shape itself. Its body is compressed laterally into a thin reflective blade, nearly invisible when viewed head-on. Silver flanks scatter ambient light unevenly like fractured mirrors, preventing a clear outline from forming in the water. Along the ventral surface, the photophores remain arranged in disciplined rows, each producing light adjusted to depth and surrounding brightness. The fish does not merely hide in darkness. It actively manufactures invisibility around itself. Other animals abandoned opacity altogether. Throughout the mesopelagic, copepods, amphipods, larval fish, transparent shrimp, and drifting gelatinous organisms survive through the near-complete absence of visible structure. Their tissues contain little pigment and scatter minimal light. Organs become translucent. Muscles fade into watery outlines. Entire bodies resemble suspended glass more than flesh. A passing predator may look directly through an animal without realizing it exists. Some species evolved stranger solutions still. The barrel-eye fish, Macropinna microstoma, drifts almost motionless through the water with its eyes enclosed inside a transparent, fluid-filled dome. The green spheres visible within the dome are not external organs, but the actual rotating pupils, capable of tracking prey above the fish, while the rest of the body remains still. The transparent shield surrounding the eyes protects delicate visual tissue while preserving visibility through dim overhead light. Predators in the twilight zone adapted invisibility into weaponry as well. Dragonfish of the family Stomiidae produce bioluminescence at far red wavelengths beyond the visual range of most mesopelagic animals. Their prey remain unable to detect the light illuminating them. In a world where nearly every organism shares the same narrow band of blue sensitive vision, dragonfish evolved private illumination systems invisible to surrounding life. The viperfish solved the problem differently. Its teeth grow so long that they cannot fit inside the closed mouth. Instead, they curve outward along the jawline like pale hooks suspended in darkness. During a strike, the fish lunges forward at high speed, while the first vertebra behind its skull functions as a shock absorber, stabilizing the impact as the jaws close around prey. The teeth form less a mouth than a cage that snaps shut before escape becomes possible. Even defense became luminous. Certain twilight zone shrimp release clouds of glowing fluid into the water when threatened, surrounding predators in drifting bioluminescent haze, while the shrimp disappears back into darkness beyond the illuminated plume. None of these adaptations emerged in response to submarines, cameras, or scientific observation. They developed through interactions between mesopelagic organisms themselves across evolutionary timescales stretching back hundreds of millions of years. Every improvement in concealment altered predator behavior. Every improvement in detection reshaped camouflage in return. The Twilight Zone became an endless evolutionary contest conducted without sunlight, where life survived not by dominating the darkness, but by becoming indistinguishable from it. Far beneath the reach of waves and weather, there are regions of the Twilight Zone where the water itself begins to thin in a different way, not in temperature or pressure, but in breath. Oxygen, dissolved invisibly through the ocean, becomes so scarce that entire layers of the water column approach conditions lethal to most complex life. These regions are known as oxygen minimum zones, though within the mesopelagic, they behave less like zones and more like submerged borders, dividing survivable ocean from biological suffocation. They form slowly from the remains of life above. Organic particles sink continuously from surface waters, drifting downward as fragments of dead plankton, waste, mucus, and microscopic debris. Bacteria feeding on this descending material consume oxygen as they decompose it. In some ocean regions, the rate of consumption exceeds the rate at which circulation can replenish fresh oxygen from elsewhere. The balance tips gradually until the water enters a state of near deprivation. Across parts of the eastern Pacific, the Arabian Sea, and sections of the Indian Ocean, oxygen concentrations fall below levels most aerobic animals can tolerate for long. The water remains chemically stable and physically clear, yet for many organisms, it functions almost like poison. Fish entering the layer begin struggling to extract enough oxygen through their gills to sustain normal metabolism. Larger predators avoid these depths entirely because the energy required simply to breathe becomes too great. And so, the oxygen minimum zone becomes a refuge. Certain Twilight Zone animals evolved not merely to endure these conditions, but to exploit them. Inside the low oxygen layer, predators capable of sustained pursuit often cannot follow. The result is a hidden sanctuary, enclosed by physiological limits rather than physical barriers, an oxygen moat suspended inside the ocean. The jumbo squid, Dosidicus gigas, moves through this environment with extraordinary control over its own metabolism. Within the depleted waters of the oxygen minimum zone, it can suppress metabolic activity dramatically lowering oxygen demand enough to remain there for extended periods. In this slowed, physiological state, the squid hunts through water inhospitable to many competing predators, its movements unfolding within a layer where survival itself becomes selective. Certain lanternfish species use the same region differently. During daylight hours, they descend into oxygen-poor depths and enter states of metabolic depression, so extreme that researchers sometimes describe them as partially powered down. Activity slows, energy use drops. Hidden within water few predators can tolerate, the fish remain sheltered during the most dangerous period of the day before returning upward again with the arrival of darkness. Yet the boundaries of these low-oxygen regions are changing. As surface oceans warm under climate change, seawater loses part of its capacity to retain dissolved oxygen. At the same time, warming strengthens stratification between upper and deeper layers, reducing vertical mixing that would otherwise transport oxygen downward. Measurements collected across recent decades show oxygen minimum zones expanding steadily through multiple ocean basins, growing across millions of square kilometers since the middle of the 20th century. The effect on the twilight zone is compressive. Habitable space narrows simultaneously from two directions. Above, warmer waters alter temperature ranges and migration behavior. Within, the expanding oxygen-depleted layer reduces the volume where many species can survive comfortably. Entire mesopelagic communities become squeezed into thinner bands of viable habitat suspended between warming surface conditions and rising physiological stress below. The chemistry of the ocean shifts with this expansion as well. Bacteria thriving inside low-oxygen waters process nitrogen compounds differently from organisms in oxygen-rich environments. As oxygen minimum zones grow, they alter the balance of marine nitrogen cycling across broad regions of the sea. These chemical changes influence nutrient availability farther upward in the water column, eventually affecting phytoplankton productivity near the surface itself. What appears at first to be an isolated problem deep within the mesopelagic slowly reveals connections extending outward through the entire ocean system. The twilight zone is not only shaped by oxygen, it participates in regulating how oxygen, nutrients, and biological productivity circulate across the planet. And within its dim interior, regions once considered marginal are widening quietly through the water, redrawing the boundaries of where life can persist. Some organisms in the twilight zone resist ordinary definitions so completely that even describing them as individual animals becomes misleading. They drift through the mesopelagic not as single bodies but as assembled collectives, living systems composed of smaller organisms fused together into structures that blur the line between colony and creature. In the dim interior of the ocean, evolution followed pathways so unusual that familiar biological categories begin to lose their shape. The siphonophore is one of the clearest examples. At first glance, it resembles a jellyfish stretched into impossible length, trailing delicate threads through the water column. But a siphonophore is not one organism. It is a colony composed of specialized units called zooids, each genetically identical to the others, and each adapted for a single task. Some zooids digest food. Others propel the colony forward through rhythmic contractions. Others reproduce. Others exist only to sting prey. Alone, none could survive independently. Together they form a coordinated living structure, functioning as though it were a single animal. One species, Praia dubia, can exceed 40 meters in length, longer than a blue whale. Suspended through the twilight zone, its body extends through darkness like a drifting chain of translucent organs communicating chemically and electrically across extraordinary distances. Certain siphonophores trail curtains of stinging tentacles, hundreds of meters long, passive predatory nets waiting for fish, crustaceans, or larval animals to collide with nearly invisible threads suspended in open water. Pyrosomes reshape the same principle differently. These colonial tunicates form hollow cylinders composed of thousands of fused individuals joined into a single tube drifting through the mesopelagic. Some remain only a few centimeters long. Others approach the length of small buses. Every individual embedded within the colony filters microscopic particles from the surrounding water, contributing to the movement and survival of the larger structure. At night, their entire surfaces can illuminate simultaneously, producing slow pulses of bioluminescent blue drifting through darkness like submerged constellations. Salps appear simpler at first, soft barrel-shaped filter feeders carried gently by ocean currents. Yet, they reproduce through cloning, linking themselves into long chains that may extend for remarkable distances through the water column. A single salp chain can filter enormous volumes of seawater every day, extracting microscopic phytoplankton and organic particles with astonishing efficiency. During bloom events, salp populations expand so rapidly that they can strip vast regions of surface productivity within days, transforming the biological balance of entire ocean sectors almost silently. What they consume does not remain near the surface for long. Salp fecal pellets are unusually dense and carbon-rich, sinking downward through the water at extraordinary speeds. Some descend thousands of meters each day, carrying carbon rapidly into deeper ocean layers before bacteria or smaller organisms can recycle it back upward. In this way, fragile, gelatinous animals drifting almost invisibly through the twilight zone become major participants in the global movement of carbon through the sea. Even among vertebrates, the mesopelagic produces forms nearly absent from public awareness, despite their immense abundance. Bristlemouth fish of the genus Cyclothone are tiny, nearly transparent predators, only a few centimeters long. Yet they may represent the most numerous vertebrates on Earth by individual count. Across nearly every ocean basin, they drift through the twilight zone in densities reaching thousands within a single cubic kilometer of water. Entire populations move beneath the oceans continuously, while remaining almost completely unknown outside specialized oceanographic research. Then there are the ctenophores, often called comb jellies, though they are not jellyfish and share no close relation to them. Their bodies propel themselves through the water using rows of beating cilia that refract passing light into shifting rainbow bands along their surfaces. These delicate organisms belong to one of the earliest animal lineages on Earth, evolutionary branches extending deep into the history of multicellular life itself. All of these organisms are abundant within the twilight zone. They filter water, transport carbon, consume prey, recycle nutrients, and shape the biological structure of the ocean on planetary scales. Yet, most remain almost absent from the biomass calculations and carbon models used to estimate how the ocean regulates Earth's climate. The largest living space on the planet is filled with organisms that do not fit comfortably inside the categories humans first built to understand life beneath the sea. For decades, climate models treated the twilight zone as background scenery in the larger machinery of the ocean, a dim transitional layer through which carbon simply passed on its way downward. Surface waters received most of the scientific attention because that was where sunlight entered the sea and where phytoplankton absorbed carbon dioxide directly from the atmosphere. The deeper mesopelagic remained poorly sampled, difficult to measure, and absent from many of the calculations shaping modern understanding of Earth's climate system. Yet, the missing layer turned out to be one of the most important parts of the process. Near the surface, microscopic phytoplankton drift through sunlit water, converting dissolved carbon dioxide into living tissue through photosynthesis. These organisms form the base of nearly every marine food web, building fragile bodies from carbon drawn out of the atmosphere itself. When they die, fragments begin sinking downward through the ocean as marine snow, a slow, continuous fall of organic particles ranging from microscopic debris to visible clumps several centimeters across. The descent appears gentle, but the twilight zone intercepts most of it before it can ever reach the abyss. Mesopelagic animals consume the falling material continuously. Copepods graze on suspended particles. Salps filter drifting debris from the water. Lanternfish, shrimp, and countless other organisms feed on the organic snowfall moving through the water column. The carbon entering their bodies does not remain suspended lightly for long. Through digestion, the material is repackaged into denser fecal pellets that sink much faster than the original particles from which they formed. This transformation changes the entire efficiency of carbon transport through the ocean. Loose fragments of marine snow may drift downward slowly enough for bacteria and scavengers to recycle much of the carbon back into upper waters before it reaches meaningful depth. Dense pellets produced by mesopelagic organisms descend far more rapidly, carrying carbon downward before it can be consumed again near the surface. The twilight zone does not merely intercept carbon. It processes and accelerates its transfer into the deeper ocean interior. The critical stage occurs beneath the surface mixed layer, the upper region of the sea still capable of exchanging gases directly with the atmosphere through wind and circulation. When mesopelagic organisms respire, excrete waste, or die below this boundary, the carbon released there becomes isolated from atmospheric exchange for decades, centuries, or longer. Carbon transported beneath this layer effectively disappears from the active climate system on human timescales. For years, the scale of this process was underestimated because the biomass estimates underlying the models were themselves incomplete. Net trawls consistently undercounted mesopelagic life, particularly fragile and evasive organisms. As acoustic surveys and improved observations revealed larger populations than previously imagined, the calculations began changing rapidly. A study published during the late 2010s suggested the twilight zone's biological carbon pump may store several times more carbon annually than earlier climate models assumed. Since many previous estimates relied on biomass figures later shown to be far too low, the amount of carbon transported downward may also have been underestimated by comparable margins. The ocean may therefore be absorbing significantly more human-generated carbon emissions through mesopelagic processes than scientists once believed. At the same time, the discovery carried another implication. If the twilight zone helps stabilize atmospheric carbon at larger scales than expected, disruption of that system carries equally large consequences. The biological pump depends on migration patterns, oxygen levels, species composition, and the physical structure of the water column remaining sufficiently intact for carbon transport to continue. Warming oceans, expanding oxygen minimum zones, and potential industrial harvesting of mesopelagic fish all threaten to alter that balance. If less carbon reaches deeper waters, more remains near the surface where it can return to the atmosphere. Marine snow itself reflects this fragility. Some particles sink rapidly, Others drift for days while being intercepted repeatedly by different organisms along the way. The efficiency of carbon export changes continuously depending on which species dominate particular regions of the twilight zone and how warming alters their behavior. Recent modeling studies suggest continued ocean warming may reduce mesopelagic carbon transport substantially by the end of the century, releasing billions of additional tons of carbon dioxide equivalent into the atmosphere each year from processes only recently incorporated into climate science. Beneath the surface of the ocean, an enormous carbon machine has been operating quietly for millions of years, and humanity recognized its full importance only after beginning to alter it. In the twilight zone, distance behaves differently for sound than it does for light. Vision collapses quickly in the dim water below the surface, but sound continues outward through the ocean with remarkable efficiency, traveling faster and farther than it can through air. Beneath 200 meters, acoustic waves move through seawater at roughly 1,500 meters per second, carrying information across enormous expanses of darkness where visibility may extend only a few body lengths. The ocean below the surface is therefore never truly silent. It is filled with pressure waves crossing through the water continuously, overlapping and bending through layers of temperature and density invisible to human senses. Within the twilight zone lies one of the most unusual acoustic structures on Earth, a horizontal layer known as the sonar channel, short for sound fixing and ranging. In many ocean regions, it forms between roughly 600 and 900 meters deep, where water pressure and temperature combine in a way that traps sound waves within a stable corridor. Acoustic energy attempting to drift upward or downward is refracted gently back toward the center of the channel, allowing sound to travel laterally across extraordinary distances with minimal loss. For whales, the channel functions almost like a planetary communication system embedded inside the ocean itself. Blue whales produce low-frequency calls powerful enough to enter the sonar channel and travel across entire ocean basins. Sounds generated in the North Atlantic have been detected thousands of kilometers away in the South Atlantic, carried silently through darkness beneath storms and shipping routes without interruption. The strange acoustic properties of the channel became widely known during the late 20th century after hydrophones recorded a sound unlike anything previously detected. In the late 1990s, instruments positioned within the sonar layer captured an immense low-frequency signal, audible across multiple sensor arrays separated by thousands of kilometers. The sound became known informally as the bloop because of its unusual acoustic profile. For a time, its origin remained uncertain because no known biological or geological source matched the recording clearly. Later analysis suggested the signal originated from a massive ice fracture near Antarctica, an ice quake propagating sound through the Southern Ocean. Yet the event demonstrated something extraordinary about the twilight zone itself. A fracture occurring within Antarctic ice could travel acoustically across a hemisphere and remain detectable by instruments thousands of kilometers away because of the oceanic waveguide hidden inside the mesopelagic. The animals living there contribute their own sounds continuously. Snapping shrimp generate sharp acoustic pulses audible across surprising distances. Certain fish produce low-frequency grunts during spawning periods. Some squid species are suspected of acoustic signaling as well, though their behavior remains poorly documented. Countless additional sounds likely pass through the twilight zone unnoticed because no continuous global recording system exists to monitor the full acoustic year of the mesopelagic across seasons and migrations. Even the deep scattering layer alters the movement of sound itself. As billions of organisms rise and fall through the water column each day, they subtly reshape the acoustic properties of the ocean around them. Layers dense with swim bladders bend and scatter sound waves differently from the water above and below. Submarine detection systems, whale communication pathways, and scientific sonar measurements are all affected simultaneously by these living migrations moving through darkness. Into this already complex soundscape, humanity introduced industrial noise. Commercial shipping routes send continuous low-frequency vibrations through the ocean day and night. Military sonar systems pulse through deep water across vast distances. Seismic airguns used in oil exploration release intense acoustic blasts designed to penetrate beneath the seafloor itself. Many of these frequencies overlap directly with the communication ranges used by marine animals inhabiting the Twilight Zone. The result is an altered acoustic environment extending through waters whose original soundscape remains only partially understood. Long before scientists established consistent records of mesopelagic acoustics, industrial civilization had already begun reshaping them. For more than a century, engines, sonar, and exploration technologies have projected artificial sound into the ocean interior, layering human noise across one of the largest and least studied communication systems on the planet. Above the Twilight Zone, life sheds itself continuously into the water. Fragments of shell drift downward beside strands of mucus released by plankton. Transparent fecal pellets rotate slowly through the dark. Dead phytoplankton collapse from the illuminated surface in clouds, so fine they resemble dust suspended in air. Tiny molts from crustaceans descend beside bacterial clumps and dissolving tissue. Together, they form what oceanographers call marine snow, a permanent downward fall of organic material moving from the surface ocean toward the deep. The descent never stops. Every second, across every ocean basin, particles begin sinking from the world of sunlight into the interior of the sea. Yet very little of this material ever reaches the seafloor intact. The Twilight Zone intercepts most of it. As marine snow drifts downward through the mesopelagic, animals and bacteria consume between roughly 70 and 90% of the organic matter before it can continue deeper. Only a small fraction survives the passage below 1,000 meters. The rest is eaten, broken apart, respired, recycled, or transformed back into dissolved nutrients suspended within the water column itself. In this way, the Twilight Zone functions less like a corridor and more like a gate. It regulates what enters the deep ocean and what returns upward into circulation. Carbon passes through it. Nitrogen passes through it. Phosphorus, iron, and silica pass through it as well. Every particle descending from the surface encounters a living system specialized in interception. The efficiency of that system changes constantly. During colder seasons, sinking material may travel farther before being consumed. In warmer waters, bacterial metabolism accelerates and particles are recycled more rapidly. Different species communities alter the chemistry of what continues downward and what remains suspended. A region dominated by salps processes organic matter differently from one dominated by crustaceans or lanternfish. The biological gate shifts continuously with temperature, migration patterns, oxygen concentration, and seasonal blooms at the surface, far above. Now another material has entered the snowfall. Microplastics descending from the surface ocean attach themselves to marine snow aggregates almost immediately. Fibers from synthetic clothing, fragments from degraded packaging, microscopic spheres from industrial products, all become embedded inside mucus webs and organic particles. What sinks no longer consists entirely of biological material. Plastic now falls beside plankton through the Twilight Zone in enormous quantities. Filter feeders consume these particles unintentionally. Small mesopelagic fish ingest them while feeding on marine snow and zooplankton. By the early 21st century, studies sampling fish from every major ocean basin had already detected microplastics inside their digestive systems. The Twilight Zone had become part of the planet's plastic circulation system before scientists had fully understood its role in the carbon cycle. The plastic rarely continues directly to the abyss. Instead, it moves through bodies. One organism consumes it, then another consumes that organism. Fragments circulate upward and downward through the food web, traveling through migrations and predation pathways that connect the surface ocean to the deep. Larger objects descend through this world as well. When a great whale dies, its body begins a long, slow fall through the Twilight Zone. Sperm whales, blue whales, fin whales, each becomes a drifting mass of concentrated carbon and nutrients, sinking through layers filled with scavengers. Fish gather around the carcass during descent. Amphipods strip tissue from exposed surfaces. Sharks and squid feed from it in darkness before the remains ever reach the seafloor. These whale falls sustain temporary communities during their passage downward, islands of organic abundance moving slowly through otherwise sparse water. Once settled on the seabed, the remains may support specialized ecosystems for decades. Inside the body of a dead whale is a record of the Twilight Zone itself. Toxins accumulated through years of feeding remain stored within blubber and muscle. Stable isotopes preserve chemical signatures of migrations and prey. Carbon gathered from countless mesopelagic organisms continues sinking long after the whale's final breath. The Twilight Zone receives all of it: the soft remains of plankton blooms, the dust of living tissue, the debris of industrial civilization, the bodies of the largest animals on Earth. Everything falling from the upper ocean must pass through this immense interior world first, where the descent is slowed, altered, consumed, and rewritten before the deep ever sees it. Far above the Twilight Zone, sunlight still touches the sea surface in shifting silver patterns. Tuna move through warm upper water. Seals breathe cold air beneath open skies. Whales roll through waves bright enough to reflect the moon. Yet many of the ocean's largest hunters do not remain there. Each day they descend deliberately into darkness, crossing the boundary between surface life and the immense hidden ecosystem below. The Twilight Zone is not isolated from the upper ocean. It is hunted constantly by animals that evolved in light and learned to feed in the dark. Among the most remarkable are sperm whales. Beneath the surface, they descend routinely to depths between 600 and 1,000 meters, entering regions where sunlight has almost completely disappeared. A single dive may last more than 90 minutes. During descent, the whale's heartbeat slows dramatically, conserving oxygen while blood flow prioritizes the brain and essential organs. All around the animal is darkness dense enough to erase distance itself. In that darkness, the whale hunts through sound. Sperm whales generate the most powerful biological clicks known on Earth, pulses reaching roughly 230 decibels. The sound is so intense it can travel through the water column and return echoes detailed enough to reveal prey far ahead in black water. A squid the size of a football becomes visible acoustically long before it could ever be seen. The whale sweeps the darkness with sound continuously, constructing an invisible landscape from reflected pressure waves alone. Other predators descend differently. Big E tuna remain creatures of the upper ocean, fast-moving hunters built for speed near the surface. Yet they regularly dive hundreds of meters downward during daylight hours in pursuit of lanternfish and squid. Cold temperatures at those depths would slow ordinary fish rapidly, blurring vision and reducing neural performance. Big-eye tuna compensate through specialized vascular heat exchangers that conserve warmth around the eyes and brain even while the surrounding water approaches 4 degrees Celsius. Their bodies cool, but their perception remains sharp enough to hunt in dim blue water far below the sunlit layer. Elephant seals descend still farther. Tracking instruments attached to migrating individuals have recorded dives extending beyond 1,500 meters, deeper than the floor of the Twilight Zone itself. Some remain submerged for nearly 2 hours before surfacing briefly, breathing for only minutes before descending again. During long migrations covering tens of thousands of kilometers, these cycles continue day after day for weeks at a time, as though the animal belongs more to the darkness below than to the air above. Leatherback sea turtles cross the same boundary with slower movements. Their immense bodies descend toward jellyfish and salp blooms deep beneath the surface, surviving cold and pressure through extraordinary oxygen storage within their muscles. Concentrations of myoglobin inside their tissue are so high that the muscles appear almost black when examined closely. Oxygen carried within the body sustains them during long descents into water cold enough to disable most reptiles entirely. Each predator carries something upward when it returns. Energy gathered from the Twilight Zone does not remain there. Nutrients consumed at depth are transported back toward surface waters through respiration, waste, and movement. Whales feeding below eventually surface to breathe and release nutrient-rich material into upper layers of the ocean. Seals, sharks, turtles, and tuna all participate in this vertical exchange. The movement partially counterbalances the endless downward drift of marine snow by carrying deep nutrients back towards sunlit ecosystems. When industrial whaling removed millions of great whales during the 20th century, this upward transport weakened across entire ocean basins. The loss changed more than predator numbers. It altered the chemistry and nutrient circulation patterns, linking the Twilight Zone to surface productivity. Effects that ocean models continue, attempting to quantify. Six-gill sharks preserve an older rhythm still. Their broad bodies move slowly through cold mesopelagic water during daylight, resting at depths approaching 800 meters before rising toward shallower regions after dark. Their migration mirrors the movements of Twilight Zone prey in reverse, a predator shadowing the vertical pulse of the ecosystem itself. For millions of years, these descents have connected the bright surface ocean to the hidden interior below. The predators crossing that boundary do not merely feed upon the Twilight Zone. They bind distant layers of the sea together through motion, carrying energy, nutrients, and biological memory upward each time they rise again toward the light. For most of human history, the Twilight Zone revealed itself only in fragments: torn tissue inside trawl nets, brief flashes on sonar screens, damaged organisms collapsing at the surface before they could be examined properly. The deeper scientists looked, the clearer it became that the older tools were observing shadows rather than the ecosystem itself. Over the last 2 decades, a different generation of instruments began descending into the mesopelagic, designed not simply to survive the Twilight Zone, but to disturb it less while gathering information continuously across enormous distances. Some drift silently with the currents. Bioargo floats rise and fall through the ocean interior autonomously, cycling through the water column for years at a time. Thousands are now distributed across the global ocean, each one measuring temperature, salinity, oxygen concentration, chlorophyll levels, and particle density during repeated descents through the mesopelagic. When the instruments surface, they transmit their collected data through satellites before sinking again beneath the waves. Unlike research ships confined to isolated expeditions, These floats remain embedded within the ocean itself, quietly recording seasonal shifts invisible to short-term surveys. Other methods search for animals without ever seeing them directly. Environmental DNA sampling begins with something deceptively simple: a container of seawater collected at a precise depth. Within that water drift microscopic traces shed by passing organisms, fragments of skin, mucus, waste, and cellular debris suspended invisibly through the current. Laboratories filter the water and sequence the genetic material contained inside it. From these traces, researchers reconstruct lists of species moving through the surrounding environment. When large-scale environmental DNA surveys were conducted within the North Atlantic Twilight Zone during the early 2020s, the resulting diversity estimates exceeded decades of physical trawling from the same regions. Thousands of species signatures appeared in water samples where nets had retrieved only a fraction as many identifiable organisms. The ocean itself had been carrying a hidden archive of life all along. Other instruments attempt to measure the Twilight Zone without retrieval entirely. The midwater respirometry system, developed by researchers at the Monterey Bay Aquarium Research Institute, encloses a volume of mesopelagic water directly at depth, monitoring oxygen consumption inside the isolated chamber while conditions remain stable. Instead of hauling animals upward into lethal temperature and pressure changes, the system studies metabolism where the organisms actually live. For the first time, scientists gained a way to estimate how much oxygen Twilight Zone communities consume without destroying the environment being measured. Cameras evolved as well. Edith Witter's Eye in the Sea system abandoned the intense artificial lighting that transformed previous observations into panic responses. The camera relied instead on dim far-red illumination, largely invisible to mesopelagic animals. Organisms drifting naturally through darkness could finally be observed without triggering immediate alarm cascades. In the early 2000s, this system captured the first footage of a living giant squid deep beneath the surface, an animal discussed for centuries yet never previously recorded alive within its natural environment. Even the machines handling specimens became softer. Traditional mechanical arms damaged gelatinous animals almost instantly, crushing bodies adapted for delicate suspension within water. New silicone-based robotic manipulators flex gently around transparent organisms, retrieving fragile salps, jellyfish, and siphonophores intact for the first time. Creatures that once dissolved into unrecognizable fragments can now occasionally survive collection long enough for meaningful observation. Above and below them, acoustic systems monitor movement continuously. Acoustic Doppler current profilers track the shifting position of the deep scattering layer across seasons and changing ocean conditions, revealing migration timing changes associated with warming water and declining oxygen levels. Autonomous gliders equipped with chemical and acoustic sensors remain within the Twilight Zone for weeks, drifting through darkness while transmitting data remotely across the planet. Yet, despite these advances, the scale of the mesopelagic still overwhelms every instrument brought against it. No complete, validated census of even a single cubic kilometer of Twilight Zone water has ever been achieved. The ecosystem spans hundreds of millions of square kilometers across multiple depth layers, filled with organisms that migrate vertically each night and horizontally through shifting currents. A successful survey in one location may become obsolete days later as entire biological communities move elsewhere through the water column. The tools improved, the picture sharpened, but each new instrument revealed the same unsettling truth. The Twilight Zone is larger, denser, and more dynamic than the scientific systems attempting to measure it. Human technology is finally beginning to glimpse the structure of the hidden ocean interior. Yet the distance between observation and full understanding remains immense. At night, when the deep scattering layer rises toward the surface, the ocean briefly concentrates an enormous quantity of living biomass into reachable water. Sonar reveals dense moving bands stretching across the sea, billions of small organisms ascending together through darkness. To marine predators, these migrations are feeding grounds. To industrial fishing fleets, they increasingly resemble an untapped resource waiting below the collapse of surface fisheries. Across much of the world, traditional commercial fish stocks have already been pushed beyond sustainable limits. Decades of industrial harvesting reduced populations faster than many species could recover, leaving fishing industries searching for new targets deeper beneath the surface. The Twilight Zone, once ignored because it was too inaccessible and poorly understood, has gradually become the next frontier under consideration. Lanternfish sit at the center of this interest. Individually, they are small, often only a few centimeters long, soft-bodied, and rich in oils. Collectively, they may represent one of the largest vertebrate biomasses on Earth. Estimates suggest global mesopelagic fish biomass may range from hundreds of millions to more than 1 billion tons, with lanternfish comprising a substantial fraction of that total. Their bodies contain high concentrations of omega fatty acids, and because of their small size, they can be processed whole into fish meal, livestock feed, aquaculture pellets, and industrial oils. To commercial fisheries facing declining catches near the surface, the arithmetic appears almost irresistible. A biomass potentially larger than all existing commercial fisheries combined drifts through the upper Twilight Zone every night. Exploratory harvesting operations have already begun in some regions. Nations including Norway and Russia tested fine mesh midwater trawls capable of targeting mesopelagic layers directly. Modern acoustic systems allow vessels to track dense scattering layers with increasing precision, following migrations through darkness in real time. What was once invisible to industrial fishing is gradually becoming technologically accessible. Yet the organisms targeted by these fisheries are not isolated resources detached from the rest of the planet. They are active components of the biological systems already described throughout the Twilight Zone. Lanternfish and other mesopelagic animals transport carbon downward through feeding, respiration, waste production, and migration. Their bodies are part of the biological carbon pump, regulating atmospheric carbon exchange between ocean and air. Removing them at industrial scale would not simply reduce fish abundance. It would weaken the ocean's ability to move carbon into deeper waters. Modeling studies published during the early 21st century suggested large-scale mesopelagic fishing could reduce deep ocean carbon export significantly. Billions of tons of additional carbon dioxide equivalent might remain closer to the atmosphere as a result of disrupting these migrations and food webs. The exact magnitude remains uncertain because the Twilight Zone itself remains incompletely measured, yet the direction of the effect appears increasingly clear. The ecological consequences extend upward as well. Lanternfish form the nutritional foundation for many predators inhabiting surface ecosystems. Tuna, swordfish, dolphins, seabirds, squid, and several whale species rely heavily on mesopelagic prey during migrations and feeding cycles. Energy gathered from the Twilight Zone moves upward through these predators into surface waters continuously. Removing large quantities of mesopelagic biomass would therefore alter food availability across ecosystems far removed from the fishing grounds themselves. What makes the situation more unusual is the absence of meaningful international governance. There are currently no comprehensive regulatory systems designed specifically for industrial, mesopelagic fishing in international waters. No globally enforced quotas govern extraction. No protected zones exist across most of the Twilight Zone. Monitoring requirements remain limited, while baseline ecological measurements are still incomplete. Humanity is approaching the possibility of exploiting one of the largest ecosystems on Earth before establishing reliable estimates of how the system functions. The regions most attractive for future mesopelagic fisheries overlap closely with regions where the biological carbon pump operates most intensely, including parts of the North Atlantic, the Arabian Sea, and the Southern Ocean. In other words, the areas richest in potential industrial harvest are often the same areas most critical to long-term carbon sequestration. The machinery required to exploit the Twilight Zone already exists. The nets, sonar systems, processing vessels, and global markets are in place. What remains uncertain is whether the living migrations moving silently through the mesopelagic can absorb industrial extraction without altering climate systems and food webs that have operated continuously for millions of years beneath. The surface of the sea, long before the Twilight Zone was understood as a climate system, a migration corridor, or the largest living space on Earth, it had already begun absorbing the byproducts of industrial civilization. Much of that contamination entered the ocean quietly, descending through water that few instruments monitored and almost no one considered biologically important at the time. By the middle of the 20th century, several nations were disposing of radioactive waste directly into the sea. Containers filled with contaminated material were lowered overboard and abandoned at depth under the assumption that the ocean interior was too vast and too remote for meaningful consequences to emerge. Between the late 1940s and the early 1990s, radioactive waste from military, industrial, and research activities entered marine environments across multiple ocean basins. A significant portion settled within or passed through mesopelagic depths before the practice was eventually prohibited through international agreement. The Twilight Zone received these materials without witnesses. At the same time, synthetic chemicals such as DDT and PCBs were spreading through marine food webs globally. These compounds were chemically stable, resistant to breakdown, and strongly attracted to fatty tissue. Even after bans were introduced across many industrialized nations during the late 20th century, the chemicals persisted inside ocean ecosystems for decades. They continue to persist there now. Mesopelagic organisms sampled today still contain measurable concentrations of these compounds because the chemicals move upward through food webs faster than they degrade. Tiny copepods absorb contaminants suspended in the water or attached to organic particles. Lanternfish consume the copepods. Tuna consume the lanternfish. Sperm whales feed repeatedly on mesopelagic prey over lifetimes, lasting many decades. At each transfer, the concentration increases. This process, known as bioaccumulation, transforms the Twilight Zone into a concentrating system for industrial pollutants. The surrounding seawater may contain contaminants at extremely low levels, yet predators feeding at the top of the mesopelagic food web can accumulate concentrations thousands of times greater than the water around them. The vertical migration accelerates the distribution further. Mesopelagic animals feeding at depth rise toward surface waters each night, carrying pollutants within their tissues. Contamination absorbed deep below does not remain isolated there. It is transported upward continuously into ecosystems supporting seabirds, marine mammals, and commercial fisheries connected ultimately to human diets. The Twilight Zone has therefore become part of the global circulation system for persistent industrial chemicals, even though its ecological structure was barely understood while much of that contamination entered the ocean. Now, another form of disturbance approaches from below. Deep-sea mining operations proposed for parts of the Pacific seafloor target polymetallic nodules rich in nickel, cobalt, manganese, and rare earth elements. Harvesting these deposits would require large industrial machines moving across abyssal sediments beneath the Twilight Zone itself. The extraction process is expected to generate enormous sediment plumes, clouds of disturbed particulate matter rising upward through the water column. Modeling studies examining proposed mining regions, such as the Clarion-Clipperton Zone, suggest these plumes would likely penetrate into mesopelagic depths rather than remaining confined near the seafloor. Fine suspended particles could alter light transmission, water chemistry, bacterial communities, and feeding behavior across large sections of the Twilight Zone simultaneously. The exact consequences remain uncertain because baseline measurements for many mesopelagic ecosystems do not yet exist. Scientists are attempting to evaluate disturbances within a system that was never comprehensively measured before industrial pressure began reaching it. That absence of baseline data may be one of the most irreversible aspects of the problem. There is no technology capable of removing persistent pollutants from hundreds of millions of cubic kilometers of ocean interior. Once they disperse through the water column and food web, radioactive particles settle into sediments or circulate through organisms. Synthetic chemicals bind to tissue and migrate upward through predators. Microplastics fragment into smaller particles and continue moving through marine snow and biological transport systems indefinitely. What enters the Twilight Zone tends to remain there on human timescales. Even the monitoring systems capable of detecting many of these changes are still incomplete. Continuous mesopelagic observatories remain rare. Long-term chemical records are sparse. Many contaminants entered the Twilight Zone decades before the instruments required to measure their effects existed at all. As a result, portions of the damage may never be reconstructed fully. The hidden ocean interior was altered before humanity understood what it was altering, and some of those changes passed silently into the darkness without ever being recorded. The Twilight Zone once changed at the pace of geology and evolution. Water masses shifted across centuries, oxygen levels drifted slowly through natural cycles, and animal migrations followed rhythms shaped over millions of years. Now the timing is different. Heat added to the atmosphere within a few human generations is moving downward into the ocean interior, reaching depths once thought insulated from rapid surface change. Since industrialization began, the ocean has absorbed the overwhelming majority of excess heat generated by greenhouse gas emissions. Much of that energy entered surface waters first, spreading gradually across currents and basins before beginning a slower descent into deeper layers. Early climate models assumed this penetration into the mesopelagic would happen cautiously, buffered by the immense thermal inertia of the sea. Measurements collected over recent decades revealed a different reality. The heat is arriving faster than expected. As surface waters warm, the density contrast between upper and deeper layers weakens. Warm water resists sinking. Cold water struggles to rise. The ocean becomes more stratified. Arranged into increasingly isolated layers, that exchange less material with one another. Oxygen, nutrients, and organic particles no longer circulate vertically with the same efficiency that shaped earlier ocean conditions. Inside the twilight zone, this weakening exchange has immediate consequences. Oxygen, consumed by bacteria and animals, is replenished more slowly from above, while decomposition continues uninterrupted. The oxygen minimum zones that already pressed against mesopelagic ecosystems have therefore expanded outward across multiple ocean regions since continuous measurements began during the 20th century. Areas once marginally breathable for many species are becoming chemically hostile, narrowing the habitable bands through which the nightly migrations move. Some species are already adjusting their schedules in response. The ascent toward surface waters now begins earlier in the evening for certain temperature-sensitive populations. Descents stretch later into the morning darkness. These shifts may appear subtle, measured against a clock, yet the migration depends on extraordinary synchronization between light levels, predator visibility, and the availability of prey near the surface. A change of minutes alters exposure to predators hunting by sight. It alters feeding opportunities. It alters energy budgets repeated every night across entire lifetimes. The food entering the twilight zone is changing as well. Warming oceans increasingly favor smaller phytoplankton species in many regions. Larger plankton cells tend to form heavier aggregates after death, sinking quickly into deeper water. Smaller cells produce lighter marine snow, delicate particles that descend slowly and spend more time suspended within the upper ocean. During that longer descent, mesopelagic animals and bacteria intercept a greater fraction before it reaches depth. The biological carbon pump, therefore, becomes less efficient, not because it stops functioning, but because the material moving through it changes shape and speed. Long sonar records, maintained by research institutions, reveal another subtle transformation. In several ocean basins, the deep scattering layer now appears measurably shallower than it did decades earlier. Part of that compression reflects warming water expanding downward from above. Part reflects oxygen minimum zones rising upward from below. Together, they narrow the vertical territory available to mesopelagic communities. The animals remain present, but within a thinner band of survivable water. Modeling studies published during recent years suggest that continued warming, equivalent to approximately 2 degrees Celsius at the ocean surface, could reduce mesopelagic carbon export significantly before the century ends. The amount of carbon no longer transported into deeper storage would equal billions of additional tons of carbon dioxide remaining within the atmosphere annually from a process absent from many earlier international climate projections. Yet even these estimates emerge from incomplete knowledge. Humanity began altering the twilight zone before its undisturbed condition had ever been measured properly. The baseline dissolved before the instruments existed to establish it. Researchers are now documenting migrations, oxygen loss, biomass shifts, and chemical transformations inside an ecosystem already responding to decades of accumulated warming. The work resembles entering a vast library after part of the archive has burned quietly in darkness. Enough remains to reveal the scale of what once existed, but not enough to reconstruct every missing page. And still the changes continue, spreading through water that covers most of the planet, moving silently beneath the surface each night while the interior ocean rearranges itself faster than science can fully follow. Long before satellites mapped the sea surface and autonomous instruments drifted through the mesopelagic, the deep ocean existed in fragments, assembled from weighted ropes, damaged nets, and brief glimpses hauled upward through darkness. The map of the Twilight Zone was not drawn all at once. It emerged slowly from expeditions separated by decades, each voyage discovering that the ocean beneath the known world was larger and stranger than the previous generation believed possible. In 1872, HMS Challenger departed England carrying an unusual mission for its era. Rather than transporting cargo or projecting naval power, the vessel sailed to study the ocean itself. Over nearly 4 years, the expedition crossed every major ocean basin, lowering sounding lines thousands of meters into water no human had ever measured systematically. Nets and dredges returned animals from extraordinary depths, many broken apart during ascent, many unlike anything previously catalogued. At the time, the British naturalist Edward Forbes had argued that life disappeared below approximately 600 meters, an idea known as the Azoic Zone theory. The Challenger expedition quietly dismantled that belief. Organisms arrived from depths exceeding 4,000 meters, proving the deep ocean was inhabited far below the reach of sunlight. The discovery altered marine science permanently, though the Twilight Zone itself remained only dimly understood, still hidden between the illuminated surface and the abyss below. More than half a century later, in 1930, William Beebe descended off Bermuda inside the bathysphere, a steel sphere suspended by cable beneath a research vessel. The chamber measured little more than a meter across. Air grew hot and stale during descent, while the surrounding water darkened beyond the small quartz viewport. At 923 meters, Beebe became the first human being to observe mesopelagic life alive within its natural environment. Through the window drifted flashes of blue and green bioluminescence, fish carrying lines of light along their bodies, translucent animals pulsing through darkness beyond the reach of surface imagination. Some colleagues on land doubted his descriptions afterward because preserved net specimens had never hinted at such living displays. The Twilight Zone appeared different when seen alive than when reconstructed from damaged remains. The decades following the Second World War brought larger international efforts. Between 1959 and 1965, the International Indian Ocean Expedition coordinated scientists and research vessels from multiple nations across an ocean basin that had previously received limited systematic study. Acoustic surveys confirmed that the deep scattering layer rose and descended not in isolated regions, but across every major ocean on Earth. The nightly migration was global, synchronized beneath thousands of kilometers of sea. By the early 21st century, expeditions no longer relied solely on nets and preserved specimens. The Malaspina expedition, beginning in 2010, circumnavigated the planet, collecting mesopelagic samples from every major basin during a continuous voyage. The resulting analyses transformed biomass estimates dramatically. Earlier calculations suggested roughly 1 billion tons of mesopelagic fish. Revised estimates approached 10 billion tons instead, an increase large enough to alter understanding of the oceanic carbon cycle itself. Around the same period, the Terra Ocean expeditions began combining genetic sequencing with physical oceanography. Rather than depending only on captured organisms, researchers filtered seawater for fragments of environmental DNA shed invisibly by passing life. Thousands of previously unknown microbial and zooplankton species emerged from water that earlier expeditions might have classified as nearly empty. Each generation of tools expanded the boundaries of the known Twilight Zone while simultaneously revealing how incomplete previous maps had been. The present decade introduced permanent mesopelagic observatories, autonomous instruments anchored at fixed depths, transmitting continuous streams of chemical, acoustic, and biological data upward through satellite networks. Yet across an ecosystem spanning most of the planet, fewer than 20 such observatories currently exist. The pattern stretching from Challenger to the present remains remarkably consistent. Every expedition entered the Twilight Zone, believing the unknown was gradually shrinking. Every expedition returned, demonstrating that the unknown was still larger than expected, waiting beyond the edge of whatever instrument had most recently been lowered into the dark. Far below the last usable sunlight, evolution abandoned many of the rules visible at the surface. Bodies became softer or more transparent, eyes enlarged beyond proportion or disappeared entirely. Mouths widened into impossible shapes. In the Twilight Zone, survival did not reward elegance in the human sense. It rewarded efficiency inside dim water where food was scarce, pressure immense, and visibility reduced to scattered flashes of blue light suspended in darkness. Some of the animals living there appear less like descendants of familiar fish and more like biological experiments conducted over hundreds of millions of years in complete isolation from the surface world. The deep mesopelagic anglerfish drifts through this darkness with a modified dorsal spine extending from its head like a fishing rod. At the tip hangs the esca, a bioluminescent lure produced through symbiotic bacteria and controlled flashes of living light. Prey approaching the glow encounters a mouth lined with inward curving teeth angled like hooks. Once contact occurs, retreat becomes mechanically impossible. The jaw itself unhinges with extraordinary flexibility. Some anglerfish swallow prey nearly twice their own body length, storing meals that may sustain them through long periods of scarcity where another opportunity might not arrive for weeks. Yet the reproductive strategy of the anglerfish is even stranger than its feeding anatomy. Males hatch without a functional digestive system sufficient for long, independent survival. Their existence becomes a race through darkness, guided primarily by chemical traces released by females drifting somewhere within the immense volume of the mesopelagic. If a male fails to locate a mate, his body gradually exhausts itself. If he succeeds, he bites into the female's skin and remains attached. Over time, the tissues fuse, blood vessels merge. The male's organs degenerate until little remains except reproductive tissue, nourished directly by the female's circulatory system. What began as two separate vertebrates becomes a single biological unit, a solution so specialized for the sparse Twilight Zone population that it functions nowhere else in the known animal kingdom. Nearby drift the dragonfish of the family Stomiidae, predators carrying another adaptation shaped by the peculiar optics of mesopelagic life. Most deep-sea animals perceive primarily blue-green wavelengths because those colors travel farthest through seawater. Dragonfish exploit this limitation by producing not only ordinary blue bioluminescence, but also far red light, extending beyond 700 nanometers, wavelengths effectively invisible to most surrounding species. The dragonfish therefore hunts with a private illumination system. Its prey swims unaware beneath a beam of light it cannot detect, exposed against darkness while the predator watches from concealment. The gulper eel evolved toward a different solution entirely. Its mouth expands to nearly 1/4 of its total body length, connected by flexible hinges capable of opening at astonishing angles. The eel does not pursue prey through rapid swimming. Instead, it drifts through open water with an enormous expandable jaw prepared for rare encounters with large food items. When opportunity appears, The mouth opens wide enough to engulf animals larger than the eel itself. Digestion afterward may continue for days while the prey slowly breaks down inside the stretched body cavity. Some mesopelagic shrimp navigate the darkness through sensory systems humans cannot naturally experience at all. Their eyes detect polarized light, subtle directional properties within scattered illumination that remain invisible to ordinary human vision. Bioluminescent signals, reflected or polarized through seawater, may therefore travel farther and carry more information than brightness alone would suggest. Then there is the stoplight loosejaw, Malacosteus niger, whose lower jaw lacks a conventional floor entirely. Bone forms an open framework beneath the mouth, with minimal tissue connecting it to the throat. This unusual structure allows the fish to strike rapidly without generating strong pressure waves ahead of the attack. In the sensitive fluid environment of the Twilight Zone, even tiny water movements can warn prey of approaching danger. The loosejaw evolved to hunt almost silently. None of these animals are evolutionary accidents, scattered thinly through empty water. They form much of the dominant predator community within the largest living space on Earth, ruling a habitat extending across entire ocean basins beneath the surface world. And despite all the expeditions, observatories, and instruments lowered into the mesopelagic, most of these creatures have still never been observed alive by human eyes outside brief encounters in the drifting dark. In the Twilight Zone, darkness is never complete. Water that appears empty through ordinary human vision is threaded with flashes, pulses, glows, and drifting lines of blue-green light appearing for fractions of seconds before vanishing again into black water. Nearly every direction contains some living source of illumination. The deeper one descends into the mesopelagic, the more the ocean begins to resemble a moving night sky suspended inside itself. Approximately 76% of Twilight Zone animals produce their own light, a proportion unmatched anywhere else on Earth. Tropical coastlines where plankton ignite beneath breaking waves appear luminous to human eyes because they are viewed from the surface. Coral reefs glow beneath ultraviolet light through fluorescent proteins. Certain bays in Puerto Rico shimmer with concentrated dinoflagellates, yet none of these environments approach the mesopelagic in the sheer dominance of bioluminescence as a survival system. Here, light is not decoration, it is infrastructure. The chemistry underlying this illumination depends most commonly on a reaction between luciferin and luciferase, a molecule and an enzyme combining to release photons with almost no wasted heat. The resulting glow is known as cold light, extraordinarily efficient compared to human technology. A deep-sea flash converts chemical energy into visible light with an effectiveness that modern engineered LEDs only partially approach. But bioluminescence is not one invention shared across ocean life. Different species evolved entirely different versions of luciferin and luciferase, arriving independently at similar outcomes through separate evolutionary pathways. The Twilight Zone, therefore, contains not a single luminous language, but dozens layered together across millions of interacting species. Each species uses light differently. Lanternfish arrange photophores across their bodies in species-specific patterns, glowing from below to erase their silhouettes against faint surface illumination filtering downward. Anglerfish suspend luminous lures before enormous jaws. Certain squid pulse rapidly during escape responses, surrounding predators with bursts of confusion. Other animals flash only during mating periods, producing optical signatures recognizable only to members of their own species, drifting nearby in darkness. The twilight zone contains no fixed landmarks, no visible horizon, no stable surface reference once depth increases. In such an environment, light becomes identity, camouflage, alarm system, weapon, and orientation simultaneously. Ultra-low light cameras, lowered without artificial illumination, have recorded synchronized flashing patterns between members of the same species, separated by several meters of open water. The flashes appear coordinated, sometimes rhythmic, passing between individuals, with timing too structured to dismiss as random chemistry. Whether these exchanges represent deliberate communication or merely synchronized responses to shared environmental triggers remains uncertain. Human technology can observe the signals. It cannot yet interpret them. Alarm signaling appears especially widespread. When one animal detects danger and flashes suddenly, neighboring organisms often respond immediately with flashes of their own. The reaction spreads outward through populations in luminous waves, resembling fire alarms cascading through a darkened city. Researchers observing remotely operated vehicles have documented these propagating chains moving across observation fields with astonishing speed, potentially warning animals hundreds of meters away within seconds. Some organisms deploy more elaborate strategies. Certain deep-sea ostracods release clouds of glowing mucus when threatened, ejecting bioluminescent slime directly into the surrounding water. A pursuing predator passing through the cloud becomes illuminated itself, transformed into a visible target for even larger hunters moving through the darkness nearby. Much of this chemistry remains poorly understood because studying it outside the mesopelagic is extraordinarily difficult. The molecules responsible degrade rapidly after death. Animals retrieved to the surface experience catastrophic pressure changes that damage tissues and disrupt metabolic systems. Maintaining living twilight zone organisms at approximately 4 degrees Celsius and pressures approaching 100 atmospheres while preserving normal biochemical activity exceeds the capabilities of most laboratory systems. Even now, the largest luminous ecosystem on Earth remains partially hidden not because its inhabitants refuse to reveal themselves, but because their signals evolved for water conditions human beings can barely enter and cannot permanently inhabit. Across the immense interior ocean, countless exchanges of living light continue every night, messages transmitted through darkness in a language older than humanity and still largely unread. The descent into the twilight zone is also a descent through temperature. Near the upper boundary, tropical waters may still carry some lingering warmth from the surface ocean above. A few hundred meters deeper, that warmth begins to collapse rapidly through the thermocline until the surrounding sea settles near 4 to 6 degrees Celsius, cold enough to alter the behavior of chemistry itself. Nothing living there escapes this influence. Every heartbeat, every muscle contraction, every nerve impulse depends on biochemical reactions occurring inside cells. Those reactions are governed by enzymes, folded proteins whose shapes determine how quickly molecules can interact. In warmer water, the reactions proceed efficiently. As temperatures fall, molecular motion slows, and ordinary metabolic systems begin to fail. A surface fish, transported suddenly into near-freezing mesopelagic water, would not simply become sluggish. Its metabolism would begin shutting down almost immediately. Muscles would respond poorly. Digestion would stall. Neural signaling would weaken. The chemistry sustaining life near the surface becomes increasingly incompatible with cold darkness below. Twilight zone species solve this problem not through insulation or heat production, but through molecular redesign. Their enzymes possess subtly different structures than those of related surface organisms. The reactions remain fundamentally the same: yet the proteins catalyzing them evolved shapes optimized for cold water conditions. These psychrophilic enzymes continue functioning efficiently near 4 degrees Celsius, where ordinary metabolic systems would slow toward paralysis. The adaptation operates invisibly, at scales far smaller than a cell, yet it determines whether an animal can survive at depth at all. Cold reshapes the body even more deeply through cell membranes. Every living cell depends on membranes remaining flexible enough to regulate nutrients, waste products, and chemical signaling. Membranes constructed from the same lipid composition as warm water animals would stiffen dramatically in the twilight zone, approaching a semi-solid state incompatible with normal function. Mesopelagic organisms compensate by incorporating greater proportions of unsaturated fatty acids into their tissues. These molecules maintain fluidity at low temperatures because their chemical bonds prevent tight packing. The effect resembles a molecular antifreeze distributed through every membrane in the body, preserving flexibility within cold water that would rigidify ordinary cells. Pressure complicates buoyancy as well. Most shallow water, bony fish regulate buoyancy using gas-filled swim bladders, delicate organs, allowing the animal to hover efficiently at chosen depths. In the mesopelagic, however, gas becomes dangerous. Pressure compresses it during descent and expands it violently during ascent, making rapid vertical movement physiologically hazardous. Many twilight zone fish abandon gas almost entirely. Instead, they accumulate wax esters and other lipid compounds throughout their tissues, substances less dense than seawater, yet largely incompressible under pressure. Neutral buoyancy is therefore achieved chemically rather than pneumatically. A mesopelagic fish drifts through darkness, balanced not by trapped air, but by oils stored inside its body. These lipids serve another purpose simultaneously. Food in the twilight zone arrives unpredictably. A successful hunt may be followed by long periods without feeding opportunities. Slow metabolism, combined with dense energy reserves, allows certain species to survive weeks between substantial meals, enduring scarcity through patience rather than constant activity. Cold also stretches time itself across the life cycle. Eggs develop slowly. Larvae mature gradually. Reproductive age may take far longer to reach than in related surface species. Many mesopelagic animals, therefore, live longer while reproducing less frequently, an ecological strategy suited to stable but resource-limited conditions. Yet this same slow biology leaves populations vulnerable to sudden losses because recovery proceeds over extended timescales. When researchers retrieve these animals to the surface, the transition becomes catastrophic. Pressure decreases rapidly while temperature rises simultaneously. Gas dissolved harmlessly within tissues forms expanding bubbles. Membranes adapted for cold begin malfunctioning in warmer water. Enzymatic systems calibrated precisely for mesopelagic conditions destabilize within minutes. Death often arrives before meaningful observation can begin. For this reason, many twilight zone organisms remain scientifically elusive, not because they are rare, but because the environmental conditions woven into their molecular structure cannot survive transport into the world above. The cold is not merely surrounding them. It exists within every enzyme, membrane, and biochemical pathway that makes their lives possible, binding them permanently to the deep interior ocean where those conditions have remained stable for millions of years. Long before most people had heard the phrase "Twilight Zone," there were researchers lowering instruments into darkness with almost no certainty about what would return. The water below a few hundred meters remained largely invisible to human observation, inaccessible except through fragile machines, damaged specimens, and brief glimpses through small viewports surrounded by pressure strong enough to crush steel. Yet some scientists kept going back. Edith Witter began by studying bioluminescence itself, the cold living light carried by so many mesopelagic organisms. Over time, she became convinced that the tools used to observe deep animals were distorting the behavior they were meant to record. Bright vehicle lights flooded the water with artificial signals. Startling creatures evolved to interpret sudden illumination as danger. What cameras captured was often a performance of alarm rather than ordinary life. Her response was the Eye in the Sea system, a camera platform designed to disappear acoustically and visually into the darkness. Instead of white illumination, it used dim, far-red wavelengths, invisible to most deep-sea species. For the first time, researchers could observe animals behaving without obvious disturbance from the observer itself. In 2004, deployed at roughly 900 meters, the system recorded the first footage of a living giant squid in its natural environment. For centuries, the animal had existed mostly through fragments, scars on whale skin, severed tentacles in nets, and stories exchanged between sailors. Suddenly, there it was, moving through darkness, alive and intact, not a myth but an organism suspended in cold water far below sunlight. Elsewhere, along the Pacific coast, Bruce Robison and the Monterey Bay Aquarium Research Institute built one of the longest continuous records of mesopelagic observation ever assembled. Since the 1980s, his team conducted more than 1,000 remotely operated vehicle dives into midwater ecosystems, documenting animals most earlier surveys had missed almost entirely. What emerged from those observations was not simply a longer species list, but a different understanding of the ecosystem itself. Gelatinous organisms, once considered minor components of the food web, appeared in extraordinary abundance. Transparent predators, drifting colonies, and fragile siphonophores occupied roles far more significant than traditional biomass estimates suggested. The Twilight Zone no longer resembled a sparse layer of scattered fish. It appeared increasingly as a densely interconnected living structure dominated by forms that older sampling methods could barely preserve long enough to identify. During the Malaspina expedition, Xavier Irigoyen helped analyze acoustic and biological data collected across multiple ocean basins during a single circumnavigation voyage. The resulting estimates revised mesopelagic fish biomass upward from roughly 1 billion tons to nearly 10 billion tons, a change large enough to alter assumptions embedded in climate models and fisheries discussions simultaneously. The revision did not emerge from discovering one hidden species or isolated hotspot. It emerged because previous methods had systematically underestimated what was already there. Marsh Youngbluth devoted decades specifically to gelatinous zooplankton in the waters surrounding the Bahamas, studying organisms many researchers ignored because they dissolved in nets and left little behind for museums or archives. Through patient, repeated sampling, he produced some of the first quantitative estimates of gelatinous biomass in the Western Atlantic, revealing communities far larger and more ecologically important than earlier surveys had acknowledged. None of these researchers worked within a field overflowing with funding or institutional attention. Coral reefs, polar systems, and commercial fisheries attracted far greater visibility. The mesopelagic remained difficult to photograph, difficult to explain, and difficult to justify financially because so much of its significance remained uncertain. Even now, the number of scientists focused specifically on the Twilight Zone remains remarkably small compared with the scale of the ecosystem itself. A few hundred researchers, spread across different nations and institutions, carry much of humanity's direct observational knowledge of a living space covering most of the planet. What connects their accounts across decades is a recurring pattern. Instruments return data that did not fit expectations. Nets surfaced carrying unfamiliar organisms. Cameras revealed behaviors no model had predicted. Each improvement in observation widened the mystery rather than resolving it completely. Again and again, the Twilight Zone answered careful study not with confirmation, but with revision. There is a particular kind of boundary in science that does not appear on maps or diagrams. It emerges only when instruments become too weak, observations too incomplete, and the system under study grows larger than the frameworks built to describe it. The Twilight Zone has reached that boundary repeatedly, each discovery revealing not resolution but deeper layers of uncertainty underneath. Some unknowns can at least be named. Researchers know, for example, that the total biomass of the mesopelagic remains unresolved by an extraordinary margin. Depending on the method used, estimates differ by nearly an order of magnitude. Acoustic surveys suggest immense densities of life moving through the water column each night, while traditional trawl data returns far smaller totals. Between those competing measurements lies one of the central unanswered problems in ocean science. Without a validated census method, no definitive answer exists. Every estimate remains shaped by the limitations of the instrument that produced it, whether net mesh, sonar frequency, camera sensitivity, or sampling depth. The Twilight Zone is so large and its inhabitants so unevenly distributed that even determining how much life exists within a single region becomes a problem of staggering complexity. The inventory of species itself remains unfinished. New mesopelagic organisms continue to be formally described every year throughout the early decades of the 21st century, with no indication that the pace of discovery is slowing. Some arrive as fragile specimens, retrieved intact only briefly before decompression damage begins. Others emerge through environmental DNA analysis, detected genetically before any complete body has been collected or photographed alive. This continuing rate of discovery suggests something difficult to absorb fully. The largest living space on Earth still contains animals unknown to science, not merely in inaccessible trenches or isolated caves, but in the open water beneath ordinary oceans crossed daily by ships and satellites. The uncertainty extends beyond anatomy into behavior itself. Bioluminescent flashing patterns have been recorded, passing between individuals of the same species in coordinated sequences difficult to explain as random emission alone. Some cascades propagate through populations with remarkable speed, spreading outward through darkness like silent weather systems made of light. Yet, no researcher has successfully manipulated these signals experimentally at scale within the natural environment. Whether the flashes constitute communication in any meaningful sense remains unresolved. The information content, if information exists at all, has not been translated. An ecosystem may be exchanging signals continuously across vast distances in a language human technology can barely detect and cannot yet interpret. The same uncertainty surrounds gelatinous life. Optical sensor studies conducted during the late 2010s suggested transparent organisms may be between 5 and 10 times more abundant than previous trawl estimates indicated. If those numbers are accurate globally, then much of the existing understanding of mesopelagic food webs, nutrient cycling, and carbon transport would require revision. Yet the studies remain geographically limited, difficult to replicate consistently across ocean basins with identical instrumentation. Even the structure of the Twilight Zone itself may not yet be understood correctly. Researchers still debate whether the deep scattering layer behaves as one globally connected system linked through migration and circulation, or as a mosaic of regional ecosystems shaped by local temperature, chemistry, and productivity patterns. The distinction matters profoundly for climate modeling because a unified global carbon pump behaves differently from multiple, loosely connected regional pumps responding independently to environmental change. And beneath all of these uncertainties rests another absence impossible to repair. There is no true baseline. By the time instruments capable of sustained mesopelagic monitoring began to appear in significant numbers during the late 20th century, industrial pollution, commercial whaling, persistent chemical contamination, and large-scale climate warming had already altered the ocean for generations. The earlier state of the Twilight Zone exists only indirectly, reconstructed through fragments, archived specimens, sonar records, and chemical traces carried inside living tissue. The untouched version of this ecosystem was never comprehensively measured before it began to change. These are not peripheral mysteries reserved for obscure specialists at the edge of the scientific world. They are foundational uncertainties embedded directly inside oceanography, climate science, and planetary biology. Each unanswered question reaches outward into models used to understand atmospheric carbon, fisheries stability, biodiversity, and the long future of the ocean itself. And still, beneath all that uncertainty, the migration continues each night through darkness no instrument has fully mapped, far below the storms, coastlines, continents, and civilizations of the surface world. Another system has been moving in darkness almost continuously since complex life first began to organize itself in the ocean. The Twilight Zone feels ancient because it is ancient, older than forests, older than dinosaurs, older even than vertebrates themselves. Long before fins evolved or bones hardened inside living bodies, microscopic organisms were already rising and falling through dim water in response to changing light. The vertical migration that now carries lanternfish and squid upward each evening began in far simpler creatures whose descendants still drift through the oceans today. Fossil evidence and molecular studies suggest this rhythmic movement predates the Cambrian explosion more than 540 million years ago, reaching backward into seas populated almost entirely by soft-bodied life. Even then, light-shaped survival. Organisms ascended toward surface nutrients beneath darkness and retreated downward with dawn, tracing the same invisible pathways still followed every night beneath modern oceans. The species changed. Entire branches of evolution appeared and vanished, yet the structure of the migration itself endured, repeating across geological eras, almost too vast for ordinary imagination to hold together. The surface world above it transformed repeatedly. Continents assembled and fractured apart. Ice sheets advanced across oceans and withdrew again. Atmospheric oxygen rose, fell, and stabilized. Coral reefs expanded into tropical seas, collapsed, then returned in altered forms. Through all of it, the mesopelagic remained suspended between surface and abyss, reshaping itself around each planetary transition. During the Ordovician extinction, marine ecosystems contracted under rapid cooling and collapsing sea levels. In the Devonian, prolonged oxygen depletion spread through ancient seas. The Permian extinction arrived later with catastrophic force, reshaping nearly every ecological structure on Earth. Approximately 252 million years ago, volcanic activity associated with the Siberian traps released immense quantities of greenhouse gases into the atmosphere. Ocean temperatures climbed, oxygen levels fell, acidification spread through marine systems. Surface waters in many regions became lethally warm and chemically unstable for immense stretches of time. An estimated 96% of marine species disappeared. Yet the Twilight Zone did not vanish entirely. Its communities contracted, reorganized, and retreated into whatever environmental refuges remained survivable. Some lineages disappeared forever. Others persisted in diminished populations through intervals lasting millions of years. When planetary conditions gradually stabilized, mesopelagic ecosystems expanded again from the remnants that endured. The same pattern repeated after later extinctions. During the Triassic catastrophe, during the event that ended the reign of non-avian dinosaurs at the close of the Cretaceous, the surface ocean suffered dramatic collapse, while deeper migratory systems eventually reassembled themselves from surviving forms. The specific species composing the deep scattering layer today are modern. The ecological function itself may be among the oldest continuously operating biological structures on Earth. Many animals now inhabiting the Twilight Zone descend from lineages already ancient before the first human ancestor ever stood upright. Dragonfish, bristlemouths, gelatinous predators, luminous shrimp, and drifting colonial organisms represent body plans refined through tens of millions of years inside conditions of darkness, cold, and pressure. Their adaptations were not assembled quickly. They emerged through evolutionary durations so long that mountain ranges rose and eroded while those refinements accumulated cell by cell. At the same time, the carbon pump driven by their migrations has been operating quietly across geological history, carrying atmospheric carbon downward into the deep ocean long before carbon cycles were understood scientifically. For immense spans of time, the Twilight Zone helped regulate planetary climate without observation, recognition, or name. It existed before human civilization and before human language. It persisted through extinctions that erased most visible life from the planet. It survived changes in chemistry, temperature, and atmosphere severe enough to restructure evolution itself. And now, after hundreds of millions of years of continuity, this ancient system is being altered across a span measured not in epochs or millennia, but in decades. At the center of most scientific fields, there exists, somewhere, a moment of direct encounter. A biologist can walk through a forest. An astronomer can point a telescope toward visible stars. A geologist can touch exposed rock older than civilization itself. Even when instruments extend perception, the human senses still remain connected in some way to the thing being studied. The Twilight Zone resists that connection almost completely. Everything known about it has arrived indirectly, translated through machinery, lowered into darkness and pressure. No unprotected human body could survive. No diver has entered the mesopelagic and returned carrying direct memory of its ordinary life. No camera has watched it without altering behavior around the lens. No net has sampled it without crushing, rupturing, dissolving, or missing part of what passed through its mesh. Knowledge from the zone arrives damaged. A fish reaches the surface with expanded tissues and clouded eyes. A gelatinous organism vanishes into residue before classification is complete. Sonar returns an acoustic signature from a moving layer that resembles solid ground, yet no physical boundary exists there at all. Environmental DNA detects hundreds of species from traces suspended invisibly in seawater, many never directly observed alive. The Twilight Zone must therefore be reconstructed through fragments. Researchers infer migration from shifting acoustic reflections. They infer metabolism from oxygen gradients inside enclosed water samples. They infer feeding behavior from isotope ratios preserved in tissue and fecal pellets sinking through darkness. They infer abundance from sonar intensity, then compare those estimates against damaged trawl collections and optical surveys that themselves remain incomplete. In this way, mesopelagic science begins to resemble cosmology more than traditional biology. Astronomers do not touch stars directly. They interpret spectra, radiation, gravity, and faint signals crossing immense distances through space. Models of black holes, stellar interiors, and galactic evolution emerge from patterns measured indirectly at the edge of detectability. The Twilight Zone operates similarly, except the invisible world under study exists not beyond the solar system, but within the same ocean whose surface ships cross every day. The parallel carries a strange emotional weight. Human beings have mapped the continents from orbit. Satellites track storms across entire hemispheres in real time. Spacecraft have photographed distant planets and landed instruments on comets. Yet, below a few hundred meters of seawater on Earth, there exists a living environment larger than all terrestrial ecosystems combined that remains only partially visible to modern science. Every improvement in observation has complicated the picture rather than simplifying it. Better sonar revealed greater biomass. Improved optical systems exposed transparent communities hidden from standard cameras. Genetic sequencing uncovered thousands of organisms absent from physical collections. More sensitive instruments consistently expanded the scale, density, and ecological importance of the mesopelagic beyond previous estimates. That pattern creates both excitement and instability inside the science itself. If every new method reveals more than the last, then the present understanding is almost certainly incomplete. The difficulty is that no one yet knows by how much. The gap between reality and measurement remains undefined because the tools capable of fully closing it do not yet exist. Science usually advances through falsification, hypotheses tested directly against repeatable observation. In the Twilight Zone, observation itself becomes the limiting factor. Some questions cannot currently be tested because the act of measuring changes the system being measured, or because continuous observation across the necessary scale exceeds available technology. So, researchers operate in a narrow space between detection and inference, building models from evidence that arrives partial and distorted. They compare signals against signals, searching for convergence between independent methods that each contain their own uncertainties. There is something quietly profound in that process. The Twilight Zone is not hidden because it is distant. It is hidden because the conditions required for its existence prevent ordinary perception from entering intact. Pressure, darkness, cold, and scale combine into a barrier that transforms science itself into an act of reconstruction. Every map of the mesopelagic is provisional. Every biomass estimate is conditional. Every model remains unfinished. What emerges from the darkness is not the zone itself in complete form, but the outline cast by its interactions with the instruments lowered toward it. A world understood mostly through echoes, traces, and the fragile evidence that survives the journey upward. Some environments resist understanding because they are dangerous. Others resist because they are distant. The Twilight Zone resists for a different reason entirely. It is simply too large. Not large in the ordinary human sense of the word, not merely wide or deep, but dimensionally overwhelming. Spread across the global ocean between roughly 200 and 1,000 meters, the mesopelagic occupies approximately 330 million square kilometers of three-dimensional volume. Even the language used to describe it begins to fail under the weight of that scale. If each square kilometer of that volume were imagined as a city block, the Twilight Zone would form a metropolis larger than the entire surface of Earth, extending downward through cold darkness beyond any horizon the human eye could navigate. Inside that immense interior, migrations unfold nightly, carbon circulates continuously, and billions upon billions of organisms move through water that no instrument has comprehensively sampled. The problem this creates is practical before it is philosophical. No research vessel could survey more than a microscopic fraction of the zone during a human lifetime. Autonomous gliders drift slowly through isolated regions while currents rearrange the living structure around them. Nets sample narrow vertical corridors. Acoustic systems map reflections across limited frequencies and depths. Cameras observe small, illuminated windows suspended inside a volume so large that even a century of continuous observation would leave most of it unseen. The limitation is not a lack of effort. Oceanographers deploy sophisticated technologies across difficult conditions with remarkable persistence. International collaborations share data across hemispheres. Autonomous floats transmit chemical profiles from remote water masses every day. Yet the relationship between the scale of the ecosystem and the scale of the civilization attempting to measure it remains fundamentally uneven. Human science operates through finite budgets, finite ship time, finite personnel, and finite instruments. The Twilight Zone operates across planetary dimensions. The entire global investment in deep-sea research across all nations remains comparatively small, roughly $1 to $2 billion annually distributed across multiple disciplines, institutions, and ocean regions. That funding supports research into hydrothermal vents, abyssal plains, polar systems, geology, chemistry, fisheries, and mesopelagic science simultaneously. Meanwhile, the ecosystem under discussion spans most of the planet. For comparison, the James Webb Space Telescope required approximately $10 billion to design, construct, launch, and operate. Its mirrors now observe galaxies whose light began traveling toward Earth before human civilization existed. Yet the living oceanic interior beneath ordinary shipping routes, inside the atmosphere of the same planet from which the telescope launched, has never received sustained investment remotely comparable in scale. The contrast is not an argument against astronomy. It reveals something about the structure of human attention itself. Civilizations are drawn naturally toward what can be seen clearly. Space produces images that arrive luminous and dramatic against darkness, photographs that translate immediately into public imagination. The Twilight Zone offers almost none of that. Most of its inhabitants are transparent, fragile, or invisible outside their native conditions. Its processes unfold slowly through chemistry, migration, and acoustic signals rather than spectacle. Even its importance is difficult to visualize. Carbon sequestration, oxygen gradients, acoustic propagation, and nutrient fluxes can be described mathematically, but the numbers involved become so large and abstract that they resist emotional comprehension. 1 billion tons of migrating biomass passing nightly beneath the ocean surface does not fit comfortably inside ordinary intuition. Neither does an ecosystem regulating planetary climate while remaining mostly unseen. So the twilight zone becomes invisible twice. First, physically, beneath pressure and darkness. Then, culturally, beneath the limits of imagination and public attention. This may be one of the defining mismatches in modern environmental science. An ecosystem essential to atmospheric stability, biological productivity, and ocean chemistry remains largely unprotected, not because its importance is disputed, but because its scale and invisibility place it outside the ordinary mechanisms through which societies distribute concern. The zone continues functioning regardless, carrying carbon downward through darkness every night across a living interior too large for any civilization yet built to fully observe. There are places on Earth where human beings have stood directly inside the systems they study. Forests can be walked through, storms can be entered. Even the surface of the moon has carried human footprints. The Twilight Zone remains different. It is a living world whose central events continue almost entirely unwitnessed. No person has ever remained inside the water column long enough, or safely enough, to watch a complete vertical migration unfold around them. The great nightly ascent begins beyond ordinary vision, billions of organisms rising together through cold darkness in numbers larger than any terrestrial migration on Earth. Sonar instruments detect the movement. Nets intercept fragments of it. Acoustic records trace its boundaries. Yet no human mind has directly observed the entire phenomenon from within as it happens. The migration remains known primarily through echoes. Even the cameras lowered into the mesopelagic alter what they attempt to record. Standard lights trigger evasive reactions, defensive flashes, sudden dispersal, or unnatural stillness. Transparent animals vanish from view entirely or drift away before instruments approach close enough to resolve their structure. Predators interrupt hunts. Prey abandon feeding behavior. The mere arrival of observation changes the event being observed. Siphonophores drifting through open water have never been filmed, behaving fully undisturbed in their natural environment. Their colonies extend through darkness like living threads, composed of genetically identical zooids, operating together as one coordinated organism. Every recorded encounter arrives through machinery, vibration, illumination, or pressure disturbance foreign to the animal's ordinary world. The untouched version remains hidden. Most Twilight Zone species have never been held alive and intact by human researchers. The problem is not rarity alone, it is physics. Animals adapted to immense pressure and near freezing temperatures begin failing almost immediately during ascent. Gas structures expand, cell membranes rupture, delicate gelatinous tissues collapse into transparent fragments before reaching the surface. Even advanced, pressurized collection systems preserve only a small fraction of captured organisms successfully, and many species remain too fragile for retrieval under any current method. So entire lives are inferred from damaged remains. The language of bioluminescence remains even farther beyond reach. Across the mesopelagic, flashes, pulses, glows, and luminous secretions move continuously through darkness. Some patterns appear coordinated between nearby individuals. Others spread outward through populations in rapid cascades. Certain species emit steady light, while others communicate through brief, coded intervals, invisible to human eyes, without specialized cameras. What information passes through these signals remains unknown. The system is older than humanity itself, older than spoken language, carried through hundreds of millions of years of evolution in a realm without sunlight. Long before human beings shaped words from breath, organisms in the twilight zone were already exchanging information through living chemistry and cold light. No translation exists. The total number of species inhabiting the mesopelagic also remains unresolved. New organisms continue entering scientific literature every year from trawl surveys, optical systems, and environmental DNA analysis. Entire branches of gelatinous life remain poorly cataloged because conventional nets destroy them before identification becomes possible. In some regions, the inventory of unnamed organisms likely exceeds the number formally described. The unknown population is larger than the known. Even the soundscape of the twilight zone remains incomplete. Hydrophones record fragments of whale communication, distant geological events, ship noise, biological clicks, and shifting acoustic layers bending through the SOFAR channel. Yet no uninterrupted acoustic record exists, covering a complete annual cycle across the full mesopelagic depth range of an ocean basin. An entire planetary sound environment continues partially unheard. These absences are not peripheral gaps in an otherwise complete understanding. They occupy the center of the story itself. For hundreds of millions of years, the twilight zone has migrated, communicated, hunted, reproduced, and regulated the chemistry of the planet beneath the surface ocean. Vast, luminous populations have risen nightly through darkness, while continents shifted overhead and entire evolutionary eras passed across the earth above them. Almost all of it happened without witness, beneath the familiar surface of the sea, below the waves crossed by ships and storms and migrating birds. Another ocean moves continuously through darkness. It does not appear on ordinary maps. Coastlines do not outline it. Satellites cannot photograph it whole. Yet it occupies an enormous living volume suspended between sunlight above and abyss below, a hidden interior layer wrapped around the planet like a second world folded inside the first. A stone released from the deck of a drifting vessel would fall through it long before reaching the seafloor. Somewhere beneath every calm horizon, beneath every harbor and fishing route and passing current, the twilight zone is already there, extending outward through cold water in every direction beyond the range of ordinary sight. The surface ocean receives most of humanity's attention because it reflects the sky. The twilight zone reflects almost nothing at all. It has no visible boundary from above, no color distinguishable from orbit, no image capable of containing its scale. And yet, the stability of the atmosphere overhead is connected to processes unfolding continuously inside it. The oxygen carried through coastal wind and nighttime air begins partly with phytoplankton drifting in surface waters. Those microscopic organisms absorb carbon from the atmosphere and eventually descend as marine snow into the mesopelagic. There, the twilight zone intercepts, transforms, consumes, recycles, and exports enormous quantities of organic material downward into the deep ocean. The chemistry regulating Earth's climate moves through this hidden layer constantly, whether observed or not. Nothing in the twilight zone pauses for human awareness. As evening passes across the ocean above, billions of animals begin ascending through darkness. Lanternfish leave deeper water in immense synchronized migrations. Transparent shrimp drift upward through cold layers that sunlight never reaches directly. Siphonophores extend their luminous colonies through open water. Predators follow. Filter feeders rise behind them. Entire living systems move vertically through the water column with a rhythm older than forests, older than mammals, older than humanity itself. While cities sleep along distant coastlines, this movement continues uninterrupted. somewhere beneath moonlit water. Animals carrying their own light are traveling upward at this moment through pressure strong enough to crush unprotected machinery. Many will feed near the upper boundary of darkness before descending again toward colder depths before dawn arrives overhead. Most will never approach the actual surface. Their migrations stop below the breaking waves, inside a region still concealed from direct human experience. They have repeated this cycle across geological ages. Long before human beings crossed oceans, before written language, before the first human fire reflected on coastal water, the Twilight Zone was already operating with astonishing consistency. Mass extinctions altered the species inhabiting it. Continents separated and collided above it. Ice ages advanced and retreated. Still, the migrations continued, the carbon pump continued, the exchanges of light and chemistry and predation continued beneath the visible sea. The Twilight Zone does not wait for discovery in the way ancient ruins or lost islands once waited. It is fully active already, functioning at planetary scale without any dependence on recognition, naming, or observation. Human science enters only briefly, through narrow windows created by instruments lowered into conditions they can barely survive. What has been recovered from those brief encounters remains extraordinary. Fragments of transparent organisms destroyed during ascent. Acoustic traces revealing migrations too vast to witness directly. Genetic material suspended invisibly in seawater. Brief recordings of luminous signals flashing between animals whose behavior changes the instant artificial light appears nearby. Every improvement in technology has expanded the known boundaries of the zone rather than shrinking them. Better sensors detect greater biomass. Better cameras reveal animals previously invisible. Better models uncover stronger connections to climate and atmospheric chemistry. Again and again, the Twilight Zone becomes larger, more populated, and more important than earlier understanding allowed. And still, the overwhelming majority of it remains unwitnessed. There is an ocean inside the ocean, immense and alive beneath the familiar sea, carrying ancient migrations through darkness, while the world above continues, almost entirely unaware. For most of human history, exploration meant moving outward. Ships crossed unknown seas. Expeditions pushed toward blank spaces on maps. Mountains rose above clouds and invited ascent. Polar ice drew nations toward the edges of the world. The direction of discovery was horizontal, toward horizons visible in daylight. All the while, another frontier remained directly beneath those journeys. Every wooden hull that crossed the Atlantic, every research vessel mapping currents, every submarine cable laid across the ocean floor passed above the Twilight Zone without truly entering it. Naval fleets moved over it during wars that reshaped nations. Fishing vessels crossed it while harvesting the waters above. Satellites eventually mapped the contours of the seafloor from orbit more completely than the mesopelagic itself had ever been mapped from within. The hidden layer remained there through all of it, suspended between surface light and abyssal darkness, immense and largely unwitnessed. Unlike earlier frontiers, the Twilight Zone cannot be crossed simply by arriving. A person may stand on a polar ice sheet or climb onto a summit and immediately experience the place directly with their senses. The mesopelagic resists that kind of encounter. Pressure crushes unprotected bodies. Darkness conceals structure. Cameras distort behavior. Nets destroy fragile organisms during collection. Even advanced instruments return only fragments of the whole. The obstacle is not distance alone. It is incompatibility. Understanding the Twilight Zone fully, if full understanding is even possible, will require technologies not yet built and methods not yet imagined. The history of mesopelagic science has followed a consistent pattern across generations. A new tool descends into the water column, and the known world expands immediately. Sonar revealed the deep scattering layer. Sensitive cameras revealed transparent organisms invisible to ordinary optics. Environmental DNA revealed entire communities that nets never collected. Every improvement in observation enlarged the scale and complexity of the system. The unknown repeatedly became larger than expected. This pattern has continued for more than a century and a half. Weighted lines lowered from 19th century vessels began the process. Steel bathyspheres carried the first human observers into living darkness. Autonomous floats, genetic sequencing systems, acoustic observatories, and low-light imaging instruments followed. None reduced the mystery to manageable size. Each revealed that the frontier extended farther inward than previous generations realized. And still, human activity now reaches into it faster than scientific understanding can follow. Warming oceans alter migration timing and oxygen chemistry. Industrial sound penetrates through the water column continuously. Persistent pollutants circulate through mesopelagic food webs. Fishing industries study the possibility of harvesting lanternfish and other Twilight Zone biomass at commercial scale. Sediment plumes from proposed deep-sea mining operations may eventually rise upward into waters whose ecological structure remains only partially understood. The Twilight Zone does not require human comprehension to continue functioning. Its migrations began hundreds of millions of years before the first human being existed. Its carbon pump regulated atmospheric chemistry before climate science had language to describe such processes. It persisted through extinction events that erased entire surface ecosystems. But the modern industrial world is now reaching downward into that ancient system. There is something unusual about living during a moment when the largest unexplored environment on Earth remains physically present beneath everyday life. It is not hidden on another planet or locked beyond interstellar distance. It exists directly below shipping lanes, coastlines, storms, fisheries, and drifting vessels. The ocean, covering most of the planet, contains an interior realm still operating beyond direct human familiarity. The scale of that realm resists intuition. The mind prefers landscapes with visible boundaries, horizons, and landmarks. The Twilight Zone offers none of these. It is volume instead of surface, motion instead of stillness, process instead of scenery. And every night, without interruption, the hidden world moves upward again. Billions of organisms rise through cold darkness toward dim surface waters, carrying carbon, nutrients, light, and ancient evolutionary histories through the interior of the sea. Before dawn, they descend once more beneath the visible ocean, continuing a planetary rhythm older than humanity, older than civilization, older than memory itself.